And it's went through a lot of evolutions and a lot of improvements over the years, and I've experimented and dabbled with some of them. And I don't have the latest and greatest design because what I put up initially worked so well that I had bigger fish to fry elsewhere. They worked well enough.
Yeah.
That's how that part of it started. And because I was cut off from most, this is an 80-acre farm, and I was cut off from most of it by consumers' energy here. And so I decided I needed to have a tower on the other side.
And that's the one way over here.
That's big.
Look at that. I hope I can get it all in the viewfinder. That thing goes way up there. Wow. Are you selling any sell space on that?
Here's a problem with that. I learned that you are subject to regulations that are for commercial that are far more severe than the silly hams as far as rules go. So if anything happens, if there's any kind of interference or any kind of co-channel anything with maybe public service or whatever, they will come down on you with both feet.
Yeah, and you're going to generate plenty of that.
And so if you're just a ham, they say, knock on the door and say, hey, knock it off.
Yeah.
You know,
Right.
And which I haven't had any of that. But if you were a commercial entity,
Right.
they'd come out with a couple of federal agents and say, hey, for all I knew, take you away in handcuffs or something. So I never did.
You got another tower back here.
I got the bug. I've always been, one of my Walter Mitty fantasies was get on VHF and UHF, and I finally did it. And so I have two 222 and 432 on that tower, and I also have a little omnidirectional.
Oh yeah, I see him down there. Yeah.
6 meter Omni. I don't know what to call it. I made it myself, but it's a knockoff of a commercial product.
Okay.
It's an omnidirectional antenna because my old high gain 6 element long john up there up above my dual bander is a great propagation antenna, but it is absolutely terrible for eastern. Everybody that's got a dipole that's 35 feet just kills me. It's walking over the top.
Yeah.
So that, when I found out about that, my interest is kind of waned because I'm a bit of a, I don't know, curmudgeon or whatever, but everything kind of went to digital modes. And I kind of licked the red off my lollipop on pursuing that. So.
Yeah. All right, so one rumor. So Dad, you're wrong. He never had CD antennas here. He told me that there was some windbreakers, and Jeff's like, it never happened. So this has always been a ham station. Yeah, very good.
So yeah, that's kind of a very short version. And we can take a little walk around maybe, and I can tell you some of what has happened since.
Okay, sounds good. All right, we'll go right there.
We can stand out here and talk, and you can shoot. Okay. You can be a victim. You can get out. Yeah.
So what's the shack? Stepping away the camera step. Yo, what's the shack? What's the story on that?
Oh, that's non-ham. Well, I shouldn't say non-ham radio related. That's the story. It's got a lot of spools of surplus wire and coax that I bought because I finally purchased my way out of my big barn.
So it has nothing to do with supporting this tower. Okay, cool. All right.
That's just rates of trouble, just general purpose storage.
Okay.
So 25G.
That's this one here? That's this one here? Go ahead.
And recently, when I had the means to do it later in life, I have went some effort to eliminate all my EHS guy wires. So all of my towers are now guyed with filigree, which is poly something covered Kevlar. And it does make a difference, and it's really nice from the standpoint of utility. It's obscenely expensive because it's worth it. But you can see up here, I got a little bit of a trolley on pulleys that runs up and down the guy wire. And you can't do that with EHS. Of course, you break things up with insulators, and that makes it not very handy. At the ground level, I've got a little bit of EHS pieces of grass wire.
So is this your main antenna then, or?
This is my 6 meter, 12 meter, and 17 meter. I've got a JK 12 to 17 dual bander that's really been a good performer. It's the junior version of it, which means it's fewer elements, a little shorter, a little more manageable, and it does a real credible job for the higher market. I have fan dipole for 10 meters. dipoles for 15 meters hanging off of this, and I use those for secondary antennas. That's part of my antenna learning process because I found out that there is no one best antenna. As an old friend and longtime silent Key, Charlie Dewey, W0CD, used to say, there are just more weapons for the arsenal. So that's how that, I learned slowly that sometimes the lower antenna is better, sometimes the general purpose cloud warmer antenna is better, and sometimes it's all high gain antenna.
Now how about cabling here? Is this hardline or what? I don't even recognize it.
I moved out here, I was cold, really cold. And so I had friends that worked for cable company that happened to be hams, and they were trying to get rid of some dead ends of some spools, so I got a lot of 70 ohm half and 3/4 inch hard line that's buried between these towers and the radio. And they held up well, so I never changed them. You know, it's pulling that cable in and out of the ground is a big job anyway.
Did you do it, or did you have somebody help you with that?
I did have some help with that. I had people that would kind of push the spools.
Yeah.
But, and I also had snakes that, when I started out, I didn't have a bar here. My radio room was in the Michigan basement in this place. It had about 5'9", like a hook line, and had the radio set down here. So I got cables that I don't use anymore to go between the house and this house. And, but they served me well for many years. Now, we can walk out here, and the second tower now, that's not beams anymore. It's an insulated base, 160 meters full size. Let's go check it out. The first time I made it into vertical. Yeah, sheet aluminum.
Oh my gosh!
And if you pick away all the grass clippings, you can see radials. Straight down to it. So there's about 130 quarter-wave radials going out.
So this is your ground plane.
This is my ground plane.
And the actual antenna is just it's isolated from the base, and you got these insulators here?
I don't know where this is something else that somebody else had or it's ground somehow. I originally shunt fed this, so it was grounded tower. I still feed it to 160. And I eventually, won't go into the details, but I replaced this tower. But, and I decided as long as I had to replace it, I'd go to insulated base. It eliminates a lot of issues that the shunt feed has. Wow. Like you're going to run power, you're going to have big vacuum variable capacitors or big capacitors.
Yeah.
So anyway, originally this aluminum was something a friend of mine scrounged for me that was aluminum camper top. And that didn't hold up very well. It didn't weather very well, so eventually it kind of just dissolved. And then I got a little more money then, so I went to Alro and I bought several sheets of 8-inch aluminum. Redid the base.
Yep. So you said that you were younger and you put these up by hand, right? So you were like scaling these towers using a gin hole, all that craziness.
Everything here is went up a section at a time.
All these towers that you got inviting new stuff.
None of it's new. I begged, borrowed. I haven't stolen it.
Wow.
But some of it you could say I stole because I got a really good deal.
Yeah, those days are over. Yeah.
So, and then I've also got another secondary antenna, which is a 20-meter quad loop that I got suspended off the system.
I see the pulley system here.
Yep. Yeah, and I got a catenary line that goes down to the south property line that I tie off to pull it out away, a little bit away from the 160-meter vertical portion.
Yeah.
And then between these two towers, I've got an 80-meter dipole.
Yeah.
That's a great cloud one. Well, in Michigan, QSO party or those type of North American QSO party, all those things.
Wow. Really cool.
Guide with Kelly strand. It's lighter Kelly strand because I don't anticipate ever hanging any beams. So I use the lighter stuff. This is really wonderful stuff other than the bill. This is polyurethane jacketed Philly strand, and it is very heavy.
So you go partially with standard guy wire, like the galvanized stuff, whatever it is.
Take it away from. There's a grass wire.
Okay.
Myself out of trouble on that.
Now, how did you learn all this? Or did you just kind of come up with it?
Made a lot of mistakes.
Okay.
I know. I wish I knew now then what I know now.
Yeah.
One of the big things that I tell people, anybody who's considering foolish enough to consider doing something like this, is begin with the ending in mind. Decide what you want to do, and then do it in steps. Because I moved out here, I was DX, and I found out that once you work most of DX, now you got to have something else to do on here. So the evolution is into contesting. And contesting and DX are two different things. And so you need flexibility, a lot more flexibility in what you can do with your station. Plus, I have friends that like to come out and operate, so I have to convert my single operating station into a multi-operating station. So I can see where the guys in big boys that are, that have these big multi stations, multi-two, multi-single, put an awful lot into control. You can easily put as much into control, antenna system, radio system, just the control part as you do in the equipment. From the bottom to the top, the first two antennas are 10-meter high gain. 5 element 105 VAs, and they are on the same rotor, drive shaft, swinging gate, cyclones. And the next two antennas are the same way. One bottom is 15-meter 5 element high gain. The next one up is 20-meter 404 VA. And the next antenna that's kind of odd duck there is JK antennas, 2 element 30-meter beam. That's on a swinging gate by itself. And then another 15 and 20 directly above that, they're both on the same drive. And then at the top, those are both nice. And the top element, 3 element JK 40. There are other, I've had other antennas on it up and down. Probably more than I want to even bother talking about. It's been an evolution. Right, that don't work by some, that works stuff away. Yeah. You climbed all the way up there too? That's crazy, man. I put that all up. I won't debate about that. Ham radio is not a hobby. Yeah. Wow. Really cool. What about way over there? I see the tower. That began like as an 80-meter, 80-meter quarter wave vertical, and now it's support for 40 meters. The story behind that is I had a good friend of mine, several good ones, went out and operate in some of the shows, ARL, or whatever. I had to call the government by that time. My friend, he was operating on 80 meters. He said, you need to either cut these beverages down or give me something with a little bit more gain. I can hear a lot farther than I can transmit. So I put together most people don't know someone got a 5 element vertical array out in the field there to give me a little bit of gain on 80. So that's those old, we get them, they're dirt cheap at Dayton, those aluminum military man. They got top load. That's been a really, really good antenna. That's got the best bang for the buck here. Yeah. And how is that building right now? Ham check is in the barn? Sure. Yep. You can see some of the PDCT ones out there. That's my coverage. I've got like 8 different directions, north, south, east, west, northeast, southwest, southeast, west. One of the improvements to the beverage is you can make a two-way beverage. Some smokers figured that out a long time ago, but I read it in a low band DX report by ON40UN, and I decided I would try it very well. So I don't have the latest iteration. I refine the design a lot. How they terminate them and feed them and all of that. But they worked well enough for me. I really haven't upgraded anything because I have other stuff more pressing.
How you been doing all these terrible windstorms we've had lately? Have you lost anything?
Last time I lost antennas, I had a couple of high gain 2 element 40-meter mounts I had to stack. They weren't really rated for the winds that were exposed to the ice. You put one up in the 16 area that's got some breaks, a little bit of break. Deep wind back for flying. But they outways where they load up the ice because the height a lot more ice on top end of the bottom and the wind and whatnot. One of the boom snaps on the lower port, and we had them be adding a truss tape out everything blowing. It was not. But I learned a lesson. Put those two antennas down. Just weren't suited. Good antennas, not a lot of them but they are not suited. That's when somebody said, hey, there's this guy over there. The 3JK, about JK antennas. And he's got some great antennas. My friend was doing one. I'm listening to this guy on 40 feet on that. He's got antennas himself. You might want to check him out. So that was the first real new expensive antenna I bought. Yeah. I was old enough by now. I didn't want to climb anymore than I had to young on the phone. Well, I think about they were something that somebody put down and gave me that was good serviceable condition, but I think it's like not enough paid off. Right now. That's really JK design, yeah. And the 30 40 today I buy all this stuff. He does the mechanic pretty robust. Holds up well. He's still this one? JK? Yeah. He just working now. Yeah. 199 feet, 11 inches. This one's probably about 120 feet.
Wow, a lot of work. A lot of work. Yeah, that's right. Yeah. So when you get ready to sell your house, you obviously put it on QTH.com, right?
Sell. There's man. Hold on, man. I don't think the hams. I really don't. Focus now. New generation. Parts on the air. Yep. Which I find. Well, I find. Yeah. Whatnot. You're not gonna. No. That's great. So you're using the PTO, your tractor to drive just a generator, and then that goes into the just another. Very difficult to build a whole house. Yeah. Got a great motor. Yeah. I bought the PTO. It's kind of, as I get older, it's more and more inconvenient to hook up this direction. Yeah.
So the main question is it just do the ham shack or does it do the house too?
There's house.
Okay, I thought there was to be prioritized.
That's a big contrast generator.
So are you on a well out here then?
So I just had that. I had
So that was pricey these days.
Yeah. Pricey the first time. Really pricey. They're smart. The motors are smart. You can tell when there's something wrong. Instead of cycling over, cycling. I got bearing going out there. This is something else you have to see that you probably should have seen. That's my beverage switch out of the house right there.
Okay, yeah. That's not a toll booth then. Yeah, we do like that. Oh, they don't say. They'll go out there. Those guys are going to do that.
Go to that. That goes out to that 40 meter dipole and my 80 meter. You really shouldn't risk getting stocks.
We're at the station up here. See the sensor assembly? How much wind right now? It's pretty hot out. We're going to trudge our way to the tower. Supposedly, it's kind of wet out here. It's trying to find the best path. Too cool down there. So what is this magic box?
This box is power in my cup household. These are all steers that are steered I've ever. And this is my electronic box. And that is the software button. Now this isn't white. I gotta keep it up. Right? Yep. I don't know if you and it goes out here. And the coaxial is 75. It's not wet.
Yeah, thank you.
Got these little feed on the bucket. This is pretty true, but I got one, here's my northeast, the east west, treated 4x. I also said you can't buy 16 treated 4x. Can't do something else, anything that long span was underneath it. So I had to replace these on the east-west of 9x6. Still taking that hard ground copper. Either of them. Half of those standard. Hard ground copper strand is a little less prone to corrosion.
We're going to the other tower? All right. Okay.
And I scrounged out all this stuff. So there's all my 50-75 ohm battery transformers. CHEV hard.
Are they in the wire?
No, they're eating those little green tubes in the different directions.
Oh, snacks. Yeah.
That's the one of those. You can see that that's not even changing the polarity. They want kind of what's the one. For the servo. Strap. Oh my God. Well, half the stuff that's in there is not even used. Everything goes through another single board computer. This one controls 80 meters. I ran that over here. Surprisingly, the only thing that eventually will fail is most, but they're cheap. And I put 12 volt, I got one of 240 volt. I'm trying to come up with the torque headed rotors. I got one rotor that probably due to poor mechanical design. There's certain angles that has a hard time getting over the hump. But that has to be. These are all being controlled via night control from right here, for example. But if you want to shine on that, the best one is 10 meter stack. You want to look at it. Okay. The bottom one is that's pretty much how it goes. And the only reason I put J4 is on a single motor is because I was trying to save money. If I had to do it over again, I probably would do something else. There's some mechanical complexity with making such my pen. You don't want to do that. Everything's fed here. I got you. Wow.
It doesn't do 360.
No, I would not climb this. These are not turbo, so he does have to climb these. He hasn't had to do it in a long time. Probably good time. On towers. They come down fast. Bad news.
This is my best bang for buck.
Okay. More kind of people.
Most people that are smart don't phase the right. I watched enough guys with high not know that I'm not good enough and all that stuff. Be able to do that. So this is a parasitic, like a vertical gag. So
this one right here.
All the rest are parasitic. So can't really box there, going on. That's how much the driven account. I got to come up here. You see, I got a guy with me. I got a little bit of wow.
Yeah.
So I feed that direction all the time. There's no relay, which I like. No relay. Unless they fail open or short. All of these other ones, they have a little box, a couple of relays in it. Coil. I can either open the base, which makes this invisible, and the anti-resonant. I can short it to the ground plate. I got a bunch of radios going out here. There's an aluminum plate underneath there, which makes it look like a direct. Or I can run it through a coil to ground, which makes it look like a reflector. So I gives me 4 directions depending on how I switch the relay. And it really works well.
And you control all that in check.
That's all right. I'll be able to have every single board looking at it.
Okay.
Go up and clear and get them all there.
Yeah.
And through all this stuff, there's a lot of materials, your hands on, lay your hands on.
So you have a true antenna farm. It looks like everything just grew out of the ground. Going in the shack. So Jeff said he got his chicken when he was 14. Right. Yeah. What are you making here?
Redesigned a 6 meter mountain.
Oh, okay.
I built that in 2008 and really worked good. We got 80 watts of that. Really good.
Is high voltage supplying them too?
That's why I was shooting down. We're not kind of a high age.
So this is kind of the workshop area near the building? Yeah.
Very well organized. So it's open. No, it is. It's secure.
As long as you didn't let me do something to do it. Yeah, here. Oh, okay. You know what? I had one little thing. You're looking on CW. I did not like it on sideband because there's just no power.
The company that prided itself on studio quality audio, this radio is more of a CD. And I'll make you a really good deal.
That's why Ross got it. He's got money.
Better deal than that.
This really good.
This phone, it's got, it has, I can figure out, best we can figure out the filter means a lot of these are maybe on a paint,
Those are kind of homebrew, aren't they? They're on cards.
Steel strictly was around the world a couple times, I've got to the point where I'm saying like I'm operating breathe more life into stuff. That's what you guys take for you guys to make it a
As you know, I filter all this kind of stuff. We just try to repair it. If it can't, I'll just let you fail. People love to see mushrooms. Oh yeah. No, we'll definitely get that. I'll definitely get it. They'll just beat on them. That's pretty much my go-to pattern. I did bring you one of my SKCC. I got my number. I don't think so. So it is kind of funny because I only live like 10-15 miles south of the jump, and we've never met. But he did try to track either me or my wife down. How many yeah. So I had no idea who it was. Charlie White. So the question is, I was driving that truck. Okay, so if he would consult a great guy, well, he would have followed me home. See? Let me get that out of here. So this is really cool. So I'm super happy and how do you switch all those elements and how do you know which one's which?
Automatic.
Okay. You got like a burger board over here? Burger board over here?
That's an open. I saw that. It's not any flavor to this stuff, like graph. Yeah. There's so many sketches, right? So I got to grab around what I got. What are 6 meter, 12 meter, 17 meter. All my station was back up against the wall. It's terrible. That gave me a good ground plate. All the chassis, all the same. If you look around the corner, step back with the back side of the shoulder. Those are all So I got both of them between the radios and the amplifiers, and those are all these are just for the constant change for the 80 to 40, 20, 15. I don't have these for work necessarily. Later on, I think I've got filters for everything. I don't know if I've got 30 songs. 17, I got to do the main reason I did that is
17, my 16 was so close that I didn't want to risk damaging by having so close to the filters down. And I didn't like the line, run back, see how my collars went back on full axle.
And these little homebrewed,
These are home, yes. So this is a, that's Resolutions, if I'm not mistaken. All of this stuff is, now this is N6 TV. All this TV box, Telegraph, is just extremely loud. He puts out some handy accessories for switching and whatnot. And I had to adapt what I had before, my 10-tech, to interface with the new generation stuff. So I got these W9X keyboards and various level converters and whatnot. It's really a clue, but once I don't have any RF problems. So these all follow. This enables me to hook up 4-bit band data from the K4s through this to steer all this other whatnot. See, I'm see it a lot in the past. No shielding, no nothing.
if you were to calculate your investment for this whole station, would it be $1 million, 500,000? I mean, just guess. I'm not even mad. I don't do anything to video. Yeah.
So, terrify me. I grew up with a family that was a baby boy.
I'll tell you that story off.
Anyway, a lot of stuff. You can either spend the money or you can spend the time. You say $1 million in labor?
Yeah. Oh, sure. Who's going to run the K4? That's this one here. Right.
Oh, that's the front of my KUAL. He is. So, I use a couple different logging programs. This is DX Lab, a little suite of programs which I use my purposes for general logging. And I interfaces. It's not a two-radio logger switch. Easily switch from one to the other. You can see that it's looking at this radio now. But if I want to change bands, I can click on, say, 40 meters, 7213. If I want to go to the other radio, and I want to go to 17, click on that button, take the radio to 17. One of the beauties is quite a few radios, including the K4s, they have an inhibitor, which you can utilize to protect the radios from my stupidity. So if I put this radio 40 meters along the other, I get this little inhibitor message. That means no matter how stupid you are, I'm not letting you transmit. And some of that is designed into the radio, and some of it is the interface there, the decodes mandated, and all the mandated, it'll be mandated as people closely inhibits. Doing content read that going on, and what I'm now doing is just does something. I need that.
And then operating mode is?
Eventually, this is the point where you get stuff repaired more often around here. I have them all now. I said, now I got them. I really swear this is like a 1 year ago.
And your primary mode is, I mean, CW.
Well, they made us do it. Yes. It is, it's hard. But it's also a victory.
Sure is.
And where you're fairly proficient at it, it's hard. It's really very soothing mode to operate.
You know, another thing that I like about CW is there's no bias. So if you hear somebody saying you don't know if they're black, white, woman, man, you don't know anything. You just know what those bits and dots are.
I know the women are on average more proficient.
Oh, sure.
I don't know what it is. They never embrace the CW. You don't want to play burnout. You don't want to play burnout.
Yeah.
So, anyway, all of those radios are remoteable, very flexible as far as interfacing and whatnot. I said, I think about it can be smart, have smart friends. Yep. My friend, MX, suggested he's been my, because he taught him, he's a degree beautifully ran from way back to Western, he's still attacking the veterinary profession. He's always beautiful. And he suggested whether he writes and software and adapting it to operate. Why don't we do this with a pie? Pie can be something plus.
Exactly. Especially a rapid.
So he wrote this radio software. This is from what's here in my government. And This is for my 80 meter. And so I got one of these for each radio. I've got separate coverage radios for each radio, so I can have this radio looking northwest, this is looking east. Now, I don't have that for 80 meter array, I don't have either. But I can, if I change direction on this one, select this one, I'll see it. Very cool. Very cool. That's one of those and then you have to use the DS lab software. I also use I got N1MM BX gateway tablet. I'm operating in a social device or whatever, and I launch on N1MM automatically BX keeper, so I don't have to constantly input. That's right. I can system mess that up. So anything I can automate. That's right. I did that because I started realizing we were kids. Stations, all of us had some old time that was meant to go over. And we go over there and we're trying to remember how to switch to have to flip to get out of 30 minutes. And then when I was 15 years old, I'm like, how can you not know that? Now I understand. So I have to document everything because I go back and say, well, I don't change this. How can I do the first time, the third time? That's the latest. Almost all of that is hardware. I found that hardware level is a lot more important for me than software. You just got to know what's going to happen to software.
This is operating resistant too over here, right?
That's another operating leadership right now. That's where this, anybody else can get That's like the back of the front body of the 40 of my and those yellow lines are how the rubber come out. And of course I got the dollars here and the support and dipole. I did the stand on these stand off brought it in and a good friend on the AMLI come over and operate. He's not a CW guy, he asked me if he's going to CW, I don't know, hey, so really good operator, he operates on my side, he's last. So all my antennas are optimized for CW, so I have some way to figure out some way besides tuners to get the antennas to come to more commands. So I started experimenting with fan diagrams. That's what it's just for somebody can go and what's operating.
Yeah, we should definitely arrange a time when you're going to be operating, so you can show people all this live and get it out.
Yeah, any Wednesday.
About what time is it?
1500, 1900, or 300. That's probably the most that I would say employ features.
Will you mind camera over your back while you're doing it? Excellent. What do we got here?
That's KADD in the foreground. ATAS. KDDs inside the field. You can see the difference in station. And we stay with the site of the metro. You can move around. It's that biggest darn field my 9-band DXCC plaque, which is legitimate. I didn't get my 9-band DXCC, but I printed this out and mounted it on a piece of cardinals. I know when I got my 9-band DXCC.
It's a great hobby, man. There's not too many people that are into it like this anymore. So.
We got HOAs and Woodbury County short of Mayhem. And I'm very fortunate that after 78, we're all state enforcement building anything else. Weren't getting around and plowing. Even if it were, they just live up. That's something that you have to look at. Most cams can't just decide We used to about 6 years. Our best we ever did was we ran like a foot less than foot most. Second place world. KRL, that's my favorite. That's my favorite. So here I am when I first leave out this That's right.
Very good. Super cool. Yeah, I'm definitely gonna come back when you're operating. This new generation, they don't understand this. They like to get
New technology. For me, if I was in the SUIS, it would be like somebody be again. And if you do the competitive stuff, the playing field is not level. It's always the same. Everybody's got their own limitations. So basically, you have to decide to set your own things. If you and I are both interested in operating Mission QS football. We might compare notes to see which one of us would do it. We're out doing program. That's morning. We don't necessarily stack ourselves against somebody that's on a conversation all the time against homes. That's very good. You still have your line, you still figure competitive.
So now Jeff is going to show you his favorite habit. And are you going to demonstrate this on the demo track?
Yes. That's kind of a nice feature of yes. This and that. These days it's more like the band slide. Just with banners and all. It's the only thing that I can help as far as all that company. That's the one I got every all of it.
So the favorite feed is?
CM9A. I think it's K3 that makes me put that up. Let's put this in customers. I end up boring you with conversation with somebody. Someone will call me into a manual sentence. This is a bug. And so I will. One of the guys that has great joy out of calling me this bug. It's a very distinctive sound. Everybody sounds different. So I got my sound so that I can answer him at the time. Well, it all depends. Send my hand we have. But I got a guy standing up behind he's like an SS who gets on here with his bug. So whenever he calls me, I answer him. So I've got it set up so I can switch between tab and light tab button. And I can send the both hands here. I can't send both hands to bugs. That's why I made weird orientation. And I said with this, good.
The rig select.
Also to our box down. See if I can. Do this now. But essentially, you can get full right arrow.
Very cool. So guys, we've been here for like 3 weeks. It's been great. I saw some stuff that I never knew existed. Jeff's got some super cool stuff going on. And we've been putting pressure on Scott to get on CEW. So I do plan to come back and Jeff's going to fire up one of these nets and I'm going to sit here and observe. It won't be a 2-hour video. We'll be here. So, yeah, for sure. Oh, yeah, for sure. Yeah. So I hope you guys enjoyed it. I know we actually have some great things I'm going to put back on the way. Yeah, I appreciate it, man. It's been great. We'll do it again. Before we go, I gotta say goodbye. I know. I just want to say hi. Yeah, you don't like me very much, do you? So you got your kitties at home, right? All right. You maintain control operator position number 2. So high-tech, in fact, that many companies even today are still using this same kind of idea. This radio also has the ability to receive high-fidelity AM. So together, we're going to electrically restore this radio receiver, align it, and then we see how it performs, and make it perform like it did back in the 1830s. So let's get started. Here's the code that we're going to be electrically restoring today. As you can see, for the 1930s, this is an extremely complex radio. And what's worth a lot of money with this thing is a communications receiver in a little case. They did a beautiful job of bringing this to all the original woodwork, and as you can see, the real clock down below, that gold with the real clock and the leaf, just the amount of effort put into that alone, that good, all original. So this radio is an excellent example to do electrical restoration. You can see this thing will perform. So after the restoration, this thing should perform just like it did back in the early 1930s. So everything works. All the dials and the waves. Indicators for failure, volume, and volume. So this is failure right here. Indicators on the back of the sliders here. It has a trifocal tune, electric eye. It's got all of these stuff. So actually, the way to restoration. So what I'm going to do now is I'll turn this thing around back to the cabinet open and get started. On that side of the radio, you can see that it says acoustical labyrinth. So if you look into some modern day ideas dealing with sound, you'll find that some modern companies are using something that's really similar to this design that was used back in the 1930s. Look up just a little bit. You see cardboard pipes running from the back side of the speaker down into the acoustical labyrinth. Right in the center of the speaker, right there, is an electromagnet. This is before speakers had permanent magnets. So the high voltage from the radio goes through that clock to the transformer on the corner there. The high voltage created by that transformer and rectified by that too goes through this brown wire right here into that electromagnet and it magnetizes it. So the current draw of the entire radio is usually placed upon that. Now in some designs it is a little bit schematic for this yet, so it may or may not run through that. Something will have a separate inductor in line with high voltage to filter any type of hum or anything like that. So I think the schematic here is going to be simply actually placed the electromagnet down here in electrical design. Lots of tubes on the chassis, very complex chassis from the 30s. Again, very expensive high-end receiver. So being expensive and high-end and in such good condition is going to be a lot of fun to electrically restore. It's now this thing before way back when. I bet you it performs very close to a lot of modern receivers. Alright, I've got my back side off. Here's the main screws. Lots of screws on the perimeter here. And around the two cardboard pipes that run into the labyrinth. So now this thing should just slide right out. Let's keep that in mind. Look at what's inside this thing. So, actually it came out very easy. Okay, so slide this over here for now. See that we have a port on the bottom here. And it also looks like there's a bit of a port or catch for the bottom side of the speaker as well here. So these pipes are pretty much from the 30s. And if you look, you can see actually the cap goes down that way. And there's an opening down there. You see that? And it goes through kind of a zigzag pattern through the labyrinth. So I know many of you are going to look this up. And again, you'll see some other companies that are using the same sort of idea that Robert Carlson was using in the 30s. Pretty neat stuff. Still really nice and solid. Excellent condition as well. So now what I'm going to do is disconnect the speaker. So I'm unplugging this wire from the radio chassis with the screwdriver. Because I can't service the radio unless the speaker is attached. Again, there's current going through this to the radio. So the speaker has to be there on the chassis above, which is outside the shop. So just service. So get all that taken out, get this on the bench. And we'll take a look at the chassis on the underside. That's when the real interesting stuff is. The speaker is in a really nice condition. You can see the seal on that box on the backside of the speaker cabinet there. The labyrinth, that's what we call it. Big electromagnet. It's coming off. No big deal. You can see they bent this nice piece of thick metal here. There's an arc welder tack it into place. So very nicely done. Now the paper that they're using, it almost looks like it's plasticized, which is very interesting. It doesn't feel like paper, it almost feels like plastic again because the grain of the paper is very interesting. It has a felt surround, really soft felt. The travel of the speaker is very fluid, lots of travel there. Lots of travel. There is no binding at all. It's absolutely flawless. So when you come across another speaker like this, you can actually adjust this in the center of the bottom. You can loosen this off and readjust the rest of the shims down in here and then re-tighten it back up. A big difference, especially if the coil is touching the magnet and you can listen all the nose of the kind of sound like you're talking with pinched nose. Whereas in this case, everything is very, very fluid. It's working very, very well. You can see that right here. So the speaker itself is just in absolutely fantastic condition. Again, the surround is very soft, so it should develop low frequencies very nicely. It's a really nice example of you can make a speaker with your minimal. If it gets any better than this, to tell you the truth, that speaker is just absolutely fantastic. So I'll go grab the radio chassis because all of this stuff is almost too big to fit on this bench right here. So move this up and I'll grab the radio chassis and put it inside and see what we're up against with that. Here's a look at the top side of the chassis. And as you can see, it has a lot of tubes. These are all tubes here, 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 here. There's an HDMI tube at the top. It's got this monster power transformer, which makes this chassis very heavy. And it's also difficult to get out of the cabinet because you have to bring the chassis back and then tip it forward. So you have to tip it on an angle because the dial glass on the front is so hard that it actually doesn't come up with the cabinet square. So difficult to get out and again, very heavy. Now this radio receiver has a lot of power to it and capability. So it can, I guess you could say, drive the speaker quite nicely. So these are the audio output tubes right here. You can see how big these metal tubes are. And they're 6 on 6s. So these things definitely going to produce some audio. Let's put it that way. They used a really big rectifier, 5Z3 here. This obviously has some current in it with all of these tubes. So IF transformers over here, and of course we have the antenna oscillator and RF section over here. All the tubing there's quite a job to tune this thing on. A lot of spots to tune here, and of course with the IF variable, it makes for an interesting tuning job. So see they have dials right here. You can tell it's showing at the same time. Okay, I think that's you can see the dial strings here, and you can see that you move this. Here, the volume up here. There's a light behind that. It actually shows you your volume. There's a red bar in and out. So the disc is turning in there. And then the fidelity is the same way. So the fidelity control, you can see moves up, and then it gets to about halfway, and then it hits a hard spot. You can still move it quite easy. What's happening here is there's a cam in the chassis that's moving slugs up and down inside the eye of things. We'll take a look at it shortly. There is a lot of this right here, and I haven't removed this yet. There is only one screw. So we'll discover the fun together. So let's remove this thing. Right? And it's, the bottom's even very nice. It's a very interesting choice of chassis. A nice look to it. So as I move this around, so I'm just going to move around the actual dial indicator behind here. Every meter knob on this thing because it has an actual ratcheting function inside. So it pulls it into each position of the selector switch, which moves this up and down. So it takes better force to move this. And of course, this is just a on-off switch. Potentiometer and variable resistor behind it. So what I'll do is I'll flip this thing upside down. I'm going to do this very carefully. I have to be very careful with this dial velocity. Flip it down and take a look under this hardware cover and see if anything's happened over time. It's obviously concerned there's going to be holes here, probably some filter tanks getting moved or something like that. So it looks like it's actually painted. I imagine something was sitting here. It's just been removed. Alright, let's take a look at the other side. There's only one screw in the bottom here. So obviously people have been in here before. Not me. Somebody else has been in this thing. I've worked on these chassis before. Not this one. So it's moisture resisting fiber. Across the here. No restoration's done here. Looks like it's been patched up through time. There's hardly nothing on there. There it is. Why is this here? Because what happens is these capacitors end up shorting out, becoming resistors, and they cause circuitry to really draw heavy current, and that heats up components. Components get hot, the part melts and starts to flow. See this right here, so we can car on it as well. So it's quite a reason we can use the chassis here, so it's definitely hot. This one here really hot, so hopefully that's still okay. We'll find that out when we verify the result. So the most common thing that destroys these old regular receivers is when these are purchased, people tend to grab these things and bring them home and think, oh, well, I'll just plug it in and see if it works. And do that. What happens is these capacitors end up shorting the electrolytes, and even these over and fully tight capacitors end up shorting out, and they burn components on one side of the radio, and sometimes a large power transformer that's waiting right here. So if the power transformer burns out, that's transforming these chassis, and looking around, find a replacement for the power transformer, and the actual color bands has changed on this. And let's attach to this lead a sealed tight capacitor. Sealed tight, keep the leakage in. Definitely that is all the replacement. So anyway, what destroys these things is these here things right here. So all of these have to go. This has to go. This. All of them go for. So there's a lot of them here that have to go. So what I'll do is I'll remove these things that come through the screws here. This I can here. Take these out. Nice free area to work in here. Start closing things. This is the very wide left right here. You can see a slug here and a slug right here. Move up and down with this control. So there's a tone control here. There's a variable resistor here. And then it's going down here and move this up and down. So we're going to change the fidelity. So we'll take a look at this next one. So you're probably asking why you're working on this on a bigger bench and with a workbench. Well, this being is because I don't have the 3585 being spec'd out on there. We want to look at the IF in this thing on this bench. So there are some reasons capacitors. So here's the square book Carlson. And you see these people that put this together have actually spent the time to put the capacitors in the correct way. You see outside foil mentioned here, that applies to the chassis. Outside foil applies to the chassis. And you can see here, the outside foil applies to the chassis. So they have spent the time to put this thing together correctly. So as I mentioned before, whenever you're working on a receiver like this, it's worth the time to locate the outside foil on the newer style capacitors because they are hard. And I designed a little device to do that. I've released that plans and schematics, everything for that on Patreon. So you take the capacitors, you take the outside foil, and put them in the replacement capacitors in the correct way. So you spend quite a bit of time to make sure that this is all done correctly. So you put these things out of the factory. So you want to make sure that when you're doing a restoration job, that you take as much time to do the job correctly as well. Now what I'll do is, when you start replacing all of these caps here, and when I have that done, we'll come back and we'll talk some more about this. So what I'll do in the next shot is I'll tell you the amount of time it took for me to replace all of these capacitors. I.e., okay, it's been 2 days since the last shot, or 3 days, you really can't tell me this has been 7 days in the next shot. I'll give you an idea of how long it takes me to do this. Now, I don't cut corners and do the J-hooking method. A lot of people like to do that. They're just cut the capacitor and move the capacitor and J-hook the leads together. I don't do that. I'll actually go right from the terminal tie strip and I'll put the capacitors in like they were in the factory. So I'll install them like that. That takes a little bit more time to do that. I just prefer that method. So I'll get that all underway, and then through this and start testing some of these systems. Keep some of these capacity building and testing. Getting an idea of how these things fit. I'm interested in testing these stronger curls. And the original device right there, and it's put in correctly, and then this here, it's right to the grade over here. So everything is all the people spent the time to do is correctly. And even people that were in here later on, I think it worked. Like this looks like a replacement part right here. They even put that in the correct grade too. So the technician that was in at some point there, this thing here, history did understand that it's very complicated. I'll talk more about why it's important to actually put these things in the correct way, even though the capacitors don't have it marked. Just before I start recapping this thing, which at this point looks like it much better. I was intrigued on features something done for I don't know when this is, anyways, but he's cut the capacitors here and tied some shielded lines and attached to the volume control so that you can pump some form of external sensors or something in here. So I want to return this thing back to factory spec as close as I can so we'll be able to understand how this thing sounded back in the day. So all of these modifications are always taken out. The modifications are done like this. Sometimes they introduce even though they have shielded cable just because of the actions and things like that. And I don't want to introduce any issues from other people's scale modifications like black tape computer, tape to a resistor, all this kind of stuff. So this has been done over time, and this is very common in organizing chassis like this. A lot of times you'll find yourself referring to the schematic and going, so what's being done doesn't make sense. Let's kind of figure this out. So I will show you the schematic and we'll go over this as we operates. I have already gone over the entire schematic for this one. We've seen it on the transfer a long time and explain all the parts and sections. So there's a schematic sequence going on there right now. And it will go over here as well to make sure that it's been done with explanation and so forth as well. Here the magic of the camera. What you see here is about 16 hours worth of work. Maybe half an hour or something like that. So it's been roughly 16 hours since the last video. They're all the components that have been replaced inside that chassis. And if you want to take a look at what's inside the chassis, I'll show you how I mounted all the new components. Now you may look at this and say, oh yeah, this looks like a whole bunch of parts. Why did it take 16 hours? It's actually working pretty quick. The reason being is you keep other pieces out of the way, and as you're replacing antennas, you're also testing other components that are attached to the same type. So you solder the component, and you have to go back later, test the component, and then remove some faulty resistor. So for example, if this was tied to a tube socket, this was tied to a tube socket here, well, I'm not just going to desolder the capacitor, right? I'm going to replace the capacitor and come back later on and test it. You'll find that it's faulty, and you have to desolder both of these again, remove this component, and then resolder. So there's quite a bit of time in just basically going through everything and testing all the components to make sure that they are close to value. Now, when you're replacing these components, you can optimize the design, and it's just due to the components. So we get grounds closer to where they need to be. Instead of running to a remote part of the chassis, you can actually ground it directly snapped to bypass capacitor to get it from the screen of the cathode or very close to in the chassis area. You can really optimize things, and that's just due to the component size. So for example, this capacitor here is the cathode capacitor on the 6L6 tubes. And this is located way across the chassis because of its size. And you can see it's a pretty large capacitor. So this capacitor here is replaced with this capacitor right here, one of these guys. You can see the difference in size. That is a very good temperature ratings as well, so I can mount this very close to the socket of the 6L6 and ground it right beside it, which again optimizes the design. You can carry wire all the way from the cathode to the 6L6 across the entire chassis and then come out this way far away. So things like that, and that really helps in RF service too. Now you're installing bypass capacitors in RF service, you want to keep them as close to the device as possible. You're not going to lose this beyond limits access. So you've got something else you pick up the modes and sensitive applications. So talk about that when I get the chassis here, I'm using I use the boxes all on 3% off of those things and nothing close to components. Here's another capacitor, something like this here, brand new. We'll replace this one. And so, and they even smaller than this for size capacitor. Capacitors, as you can see, size optimized as well. These are very long life capacitors that I use. So I'm doubting that these need to be replaced for extremely very high power electronics. I have a tight list. I've spent time grading countless hours grading, testing components, and verifying them. Using those radio receivers so that it keeps the radio receiver working incredibly long. I have those lists up on Patreon, a couple of those verified components lists up there on those videos. So if you're restoring videos, that would be beneficial to you because I just consider what I do. So what I'll do is I'll test some of these components here and I'll show you where the real problems were. Just by reading these components and testing, I can tell when the radio will fail. So I don't need to turn the radio on to do this. So okay, this is bad, so that means that this is bad. This is faulty, so this is the result of that being faulty. So what I'll do is I'll start experimenting. So get a schematic shot and we'll test the phase depth of the capacitor as well. So this is the capacitor that's across the AC line applied to the chassis. Now these capacitors are it's getting real strong turn out of the depth caps. Really what happens with these things is they end up short and becoming electrically leaky and bring AC line. So this is that capacitor. We'll test this as well and we'll see exactly what's going wrong. We'll explain all about all of these components here. So we'll grab a schematic, some tools here and talk about that. And then I'll grab a radio chassis and I'll tell you where I fix things and why I done it like that. Okay, so here's the schematic, and for any of you that are doing these stronger cross radios, They're very particular about these resistors that are basically sealed in the block. They don't have any resistance ratings listed anywhere, so what ends up happening is capacitors fail in these rating exams, and that resistor block goes open, and that you're left scratching your head when you run really was the resistance value. So I've taken the time to mark that off, so any of you that have a failing one of these ratings, let's see that has that burnt out resistor block, that's very common with capacitors failing. So when this fails, these are the resistance values. So there's 3 resistors inside that resistor block, and I'll show you how to do it down to the bottom of the chassis. I actually just write right on the resistor, a script that holds it down, I write the resistance values, so in the future if something does go wrong, it can very easily be replaced by something else or myself, right? So these are the values. So we have a 630 ohm resistor right at the top here, there's a 12 k ohm resistor right here, and then this resistor is completely separate. This is the capital resistor for the 6 and 6s right here. So it's 2 resistors that are put together in one separate bottom. So the values, again, I'll cover that when we get to the bottom side of the chassis, and I'll show you the resistor. I actually put a piece of thermal transfer of silicone underneath it, so that will transfer the heat to the chassis, and the chassis is meant to sit. And it also keeps it tight in the brackets. A lot of the times they come loose, it's just a plastic chain seals over the years, and you get it loose, and it's properly transfer the heat to the chassis. So I'll show you lots of things that have been done there. So this capacitor here, so there's these 2 right here, so you can see it's a common ground of the chassis. So you can exposure fixed rate, okay? Right, this is staying on right. Okay, so that's the second picture, which is the shell of this capacitor right here. This is each capacitor. Each one of these leads these things off to the line side there. Now, as you can see, this is put together properly. Stronger cars use the brain there, putting this together. You can see the very first thing in line is the fuse, and then after that is the switch, and then after the switch are the capacitors. So if this ever fails, it's not right across the line, because the line goes it's beyond the fuse, so the fuse will go away. The difference is to short across those 2 layers. A lot of new designs that don't do that, they have to fuse in other grids and things like that. You can see there's a different version of this stronger cross, and it has a full adapter, and it's kind of skyscraper ratings, pretty solid for as well. And it's even got the photograph after the fuse and switching as well. So it's protected by that first fuse and line. It's very important. So this capacitor here is replaced with a modern X1 Y2 related capacitor. So there's 2 of them, right? One for each other. They're X1 Y2, so they have very good safety limits. They're actually a certified safety capacitor. So when they fail in the correct load causation. Whereas X1 Y2 have very good safety capacitors. If you're interested in that, you can look those up. In fact, I have a bunch of those capacitors to get listed on the verified Google list. It's something you can learn after get at it. So these resistors here are the ones that I was talking about along on the back side of the chassis. And these capacitors here have all been replaced by these modern caps right here. And of course, this capacitor capacitor right here is the one that was replaced by this one right here. Alright, Google caps, long life, very important. Now, so these capacitors here. So these ones here are down here. So one of them that's down here. Alright, that's right across this particular ring right here, and right to the ground. So it's going to show it off in the center, and I'll show it tied off the ground, but it is actually tied off the ground. These caps right here, there's a few things in the parts listed that are listed, which is kind of interesting. The parts have a number on there, but they're not listed. ID and part number 175 is not listed. Things like that. Anyways, these capacitors here, this is basically a 10 kilohertz filter right here. So to keep the highs, I guess at day, you could say, because the IF on this thing is very high. It's too very low IF transformers, so it gets a very high fidelity 70 AM out of this thing. So there's a bunch of these things in here. You can see I replaced these here. Now it's kind of a little bit odd because they use 2 different types of capacitors. You can see this one says microvolt on it. Okay. So the microvolts, these 100 picofarad capacitors are leakers. Now a normal capacitor tester won't detect this. So these look fine on a normal cap tester, even on a normal voltage tester, they look absolutely fine. But these are actually great. Now there are other capacitors in the actual radio chassis that's made in Canada. I'll show you those ones there. Those ones are all okay. It's just these microvolt ones here that are a problem, especially the ones that seem to have between 8 and 16 here that was doing some work with our band switching section. So this one here, I had to remove this resistor from this one solder to test this because this would act as leaking. All these microvolts here seem to be creating a bit of an issue. So this one capacitor here was in the RF section here somewhere. Is this one here? There's this one here, and then there's a resistor across. You can see this here. This one here. So this was replaced with new microcapacitors. Let's get excited here about there's so many parts and pieces all over this. These are 47 kV resistors can be moved up in value. Capital bypass capacitor, this one here is virtually open. So they've really lost a lot of response. This capacitor here, they've really lost a lot of response. And the loudness effect of this part here is it's not very hot. Of course, that's because of failing components. This radio was being used. This radio was being used like this up until not long ago. So there have been used some components that was definitely apparent, as I mentioned before. And some of these capacitors are so incredibly bad. Some of these original capacitors in this unit are so incredibly bad. This thing was on the verge of a really catastrophic failure. So I'll replaced. So lots of parts and pieces replaced throughout this entire radio. Whenever you're working on one of these radios, there's a little part that hides by the tuning eye. It's usually right in the tuning eye cap itself. That will always should be checked. It's usually around my radio resistor. So there are discrepancies in parts lists. A lot of these radios I've noticed lots of discrepancies in this as well. So I've gone with appropriate values that make sense to other sections. Now, it could be the discrepancy that I'm seeing has been a component replaced on the technician down the line. For example, when I was looking at this didn't look right. Alright, so this 2.5 kilo resistor is actually supposed to be 560 milliamps. Alright, so there would have been quite a bit of voltage drop across this device, and it would have caused the receiver to be not as sensitive as it could be. So I replace this with the appropriate value, and of course, you have to test this thing out to see how it works. Turn it on for the first time. This value here is one of those 560 ohm resistors, so it's been very, very hot. It's because one of these capacitors was very, very weak. I believe this one here is attached to it. So this is one of those really large series type capacitors. As you can see, it's had better days. So there's another one here too. Different color, solar series type capacitor. High temperature molded capacitor that spits chunks of its molding on the top. You can see it there. At any rate, we'll just always do it. So all of these capacitors here, no matter how you test them, they're going to be bad in some way, shape, or form. You'll find some that are better than others. And they just are kind of odd because usually these capacitors are very good. You can imagine it's very good capacitors. This way you're just going to see this way it's because they know the two of them in one unit. That might actually be the issue with this. So I don't know why these are good or this one. Nice thing about the capacitors. Now I always say these things, I put them in the bag and in the box, and I can use these as reference in the future. And then people might know, okay, well, I have one of these capacitors inside the radio, so I think it would be bad. I can go these. I can go, yes, I test these things. I test them on a normal tester, and it'll be fine. But if you do an extensive test with the capacitor tester that I've created, you can really see the problem. I created that capacitor tester because I was working on transmitting and some very high voltage like the capacitors were not showing any problems on any test equipment, even modern stuff. So I had to design my own piece of test equipment to find problems, and sure enough, I found a problem. I replaced the microphone and transmitters back in service, and so anyways, I'll show you that here as well. So anyways, this is the first equipment. I'm not going to get the components here. I'll get some test equipment and I'll show you exactly why this is failing and what's going on inside. Here's a very good capacitor leakage tester that's ready to go to the most market today. It's not very sensitive and work very well. However, when testing some capacitors, they just aren't sensitive enough, even in the market position, which is the most sensitive leakage testing position that this capacitor tester has. Now, these capacitor testers, they put quite a bit of applied voltage across the device to test it. As you can see, this one here, 600 volts across the device. Keep in mind, current is low, but that is still 600 volts, and caution needs to be used whenever you're using one of these devices. So if you ever do get replaces, follow the safety instructions that are issued with the device. It's always a good idea to keep it in the discharge position. The switches aren't spring loaded, at least in this model isn't, so it won't automatically start back to discharge. You always want to make sure before you touch the leads or anything that it's in discharge, and the voltage turn right back down to its minimum. That's just a few extra safety precautions when using a device like this. Keep in mind, if you were going to purchase something like this and use it, you'll definitely do some extra manuals to be careful. This device that I've designed is a low voltage tester, so much more safer to use, and it's much more sensitive as well. It's designed to find those obscure issues, and I'll give you an example of that right now. So here's one of those capacitors that I'm taking out. That one is going to test absolutely fine, but this one here will show the failure point. So I mentioned this before, okay, in many of my videos about these types of capacitors in the oscillator and RF section. If you don't have to replace these micromodes and the capacitors in those sections, definitely don't do it. So you want to test them and make sure that they're not faulty. But if you don't have to replace them, don't just replace them for the sake of putting them on your part. The reason being, and as I mentioned in earlier videos, is at the foundry, many of these are hand-picked, and what they've done is they've optimized on the values to make the dial on the radio track the oscillator into the oscillator section. And even in the RF section, you need to be very, very careful with these caps. You don't want to be replacing these things unless they're absolutely necessary. So here's so many people say, oh, I just took out all the capacitors, and I just replaced all the capacitors and started from there. But now, 600 amp is somewhere around 650, and I just can't get it to line up. Again, a lot of these things, they were hand-picked to make sure that the dial is tracked correctly. So something that may say 100 picofarad, that's where this is right here, 100 picofarad, may not necessarily be 100 picofarad. It's hand-picked, it might be 112. Alright? So, all of them are used to see those rings, they may plot just tons of 100s, and just hand-picked out 112s, and that will be great for just keep that in mind when you're installing those on users. These should always be tested and not just the one that is replaced. Wax capacitors on buildings like this, and don't even twice ago. Okay, so I'll give you an example of this here. So what I'll do is I'll attach the test leads of this to this capacitor here. Alright? I don't want to lose leads because this thing here has told me that these leads are wildly conductive. And I don't want to touch them. So we're going to see the leads here. So I'll put this on the leakage. If this is bad, that I should close. Okay? Right up 600 volts. Shows it as being okay. Okay? Turn that back down again. Hit discharge. To show you the capacitor tester working here, put this here. Okay, put this on the leakage. And as you can see, it's just 3 volts. But it's not really it's faulty. It means it's a bit short of this one. So you can see that. I'll test the other half as well. Okay, so I'll put that over there. Right, so it's a part like so. Fall like that. Leakage. Right up to the top, 600 across it. bottom, nothing's happening. So it shows this as being like hook discharge, it goes in discharge. So I'll move this over here. Alright, so now what I'll do is I'll test this in forecasting position here. So there's two scales that are indicated by these YAVAPI. So this is a new release of the code that many patrons that have asked me to give this a larger broad scale. Now something that can be calibrated with resistance reading and this is not. So this is a more new resistance. So what I'll do is I'll put this here. All the design working in here. This is just that. This is something that is more optimized if you want to actually get an idea of the actual resistances of the device you're going to look at. So put this across here. Yeah, we'll hold the boots because the boots are not really elected and this will pick it up. So hold it back here. Okay, so this is in the forecast position. So if it's red, it's really bad. If the scale is yellow, it's on the second scale down here. It's really low. So this is discharge. Okay, so it's green. And I'll put it on the test line. Straight out. Show revolution. So it's red. Only one LED in from the end. So that's just over 1 gigawatt. Okay. So this can come all the way down here again before this goes to discharge. Let it discharge. Okay. Okay. Here we go again. This is a faulty pulse. Test the other one. Shut it off. Move this over here. Test the other capacitor over here. Okay, so here we go. Now it's just a little worse than the other one. Okay. Oh, it's coming down a little bit. Still very down. So they're very, very close together at any rate. So I have an idea of how the capacity test. So this is 100 picofarad. Okay, so if we were to test this on a normal capacitor tester, here grab a normal cap tester here, and this up here. I'll put this on a 200 picofarad scale. What you're seeing is just a typical capacitance between these two things. I'll just plug these in. So then this is the outward. I'll just plug these two into the fixture here. My hands away from it. Fit. Just fit these. Yes. There you go. There you go. See, it's in there tested 180, so I think that it's okay. The capacitance is okay, but it is turning into a resistor. So what I'll do is I'll pull this out of here, and I will give you an example. This capacitor, so this is another capacitor. This one here is 100 picofarad. Same kind of deal, right forward, right. What I'll put this one into these leads now. Keep in mind, this here is just another micro. It's like the other one, it's just a different package. Okay, so here we go. On the leads. Now watch what happens. No problems. That's me on 40 burning rooms. Shut that off. It's through the discharge stand on the test. No problems. Okay, so that's how most capacitors are. As my shear test in the forecast position. You got to know what is this one? 4900 picofarad. Okay, so this one here should be 3900. You can see what it needs on here. Make sure I'm here. So there you go, 3.87, so 3.87 nanofarad or 3900 picofarad, very close. Okay? Alright. So let's test this one. Now this one here is a little bit larger than the other. Let's test this one here on this. Okay. No problems. Again. Discharge. Here we go. No problems. So you see if I just put my finger across it. I'm sure we're going to think I'm dead shoulder. So this one's rated 0.1 microfarad. Put this on here, and the voltage. Wow. So there you go. This one's rated 6 volts. This one is rated at what? 200. This is rated at 200 volts. Alright, so this one's a really effective return. You can see what this does here. 3. Wasn't this. Still in the press position. Pull that up there. Works. For the second one, between the first and second one, we're looking at 10 megohms of resistance. This one's really bad. Yeah, it's going to be like 10 megohms of resistance. It's only one like the red, which is a bad scale. So this is really bad. So this is virtually the dead short of megohms. This is around 10 megohms are in that area. So we shut that off. That's fun, right? Let's just take a look at this. Keep in mind that those things are across the supply lines. Right? These are the ones that just destroy the radio. So turn this on. Here. See that? Alright, so here's the cap. It's read its resistance. Yeah. So it'll keep counting for a while. So now you can see the 3 megahertz right now. It'll probably settle off if I let this sit for a little bit. So So this other cap, this texture here, we actually do a quicker reading. Let's try this one. So there you go. That's 6 megohms. Almost 7 megohms. All right, here's a good point 1. So we test this. So obviously it's a whole bunch of connection, right? Right, seems open. All right. But if we test this with the other here, which goes way up into the mix. We test that with this one here. This is only apply very current. See what this does here. It's here and here. Beyond 500 megohms right there. The reason it's climbing slow is because it's charging the camera. Because beyond 500 megohms, which is absolutely fine. Of course, these things test great music awesome too. These are all identified parts. This is that radio has a ton of music over it. So at any rate, there we have an example of why you may possibly want to put something like this. So if you do want to know this, all the plans are on Patreon, you'll find out that this thing is very beneficial. I use this continually, in fact, just for fun because I'm using components. I've actually tested with this to see how bad it is. And as you can see, that was there may set it off. So let's just put 7 megohms, something like that. We'll set off or settle off around that area. The first light's about 1 megohm to short, second one hit about 10 and a bit, and the third one's going up. And this here, just about 1 gigaohm. 1 gigaohm, and then the scale flips, and you get to relative gigaohm. That's all over 40 billion ohms this tests. So if there's any leakage through moisture ingression in your capacitors or anything like that, this detects it. It's doing that thing. It's fixed to fix that transmitter. And that transmitter is, as I say, it has no problems. In fact, it's still in service. No issues whatsoever with that. Now, keep in mind, all the previous versions that you've seen to this test is pretty close to the same range as this one. This one has one extra added range, so you can see the capacitors are charging. That's why it's a bit fun. We're all of these things are pretty up there. So if you can build something like this for yourself, you can do that. And of course, the fluorescent tester is there as well. This is the test for outside 4. Example here, I do this with every single cap I'm up there. This is using every outside 4 listed. So turn this on. Hands up here, I'll insert some noise into this cap. So the LED with the least amount of LEDs lit indicates the fluorescent. So this is the fluorescent noise and noise. Okay, so the least amount of LEDs with the LED here that's lit indicates the fluorescent. Touch this second so I'm acting as the noise up there. This is up there as well. So this is an adjustable sensitivity setting for all sorts of different capacitors, and it also has an intensified position here for the really, really sensitive ones. You're having a hard time locating this up as well. You can see how just clear that is, right? So outside for this side. So then what I would do is take this capacitor here, and then take my fancy pen here, cap off, and then put a little dot here. Just like so. And that little dot now means inside 4 under this is not for use. So to give you an example, these capacitors are leaking. They will have inside 4. So you can see that this is clearly marks outside 4 on one side, outside 4. Alright, so it's here, it's here, it's here, and so this side here should be the least amount of lights again. This one will come and go. Not much. So that's the least amount of lights on that side. Using the outside 4 isn't as pronounced on this one. Pronouncing the outside 4 sensitivity as well. So least amount of lights, corresponding LED is the outside 4. And it's this side right here. As you can see, it says outside 4. So focus on that, you'll see the effect on the other side. Okay, so remove this, turn this around, so this should be the least amount of LEDs. So using the outside 4 on the side. Yeah? So it's working on that. Again, very useful for you to hear these things in the correct way, especially for bypass service and things like that as well. We have a project that's up there, ready for you to build with all the plans and schematics and everything. So it's just 2 of them. I have a lot of things and devices up there that I design. So if you feel like these have been beneficial to you, maybe come in and check those out. For those of you that have been in situations like this, they reach the same resistors. It's in the coding is a little bit different. So if you do remember bed or bell, you can very easily decode these resistors in the future. Bed is very easy to remember. Body and dot, or bell as a body and line. So the body is the majority of the color. So the body is yellow on this, which is 4. The end is purple, which is 7. And then the line is orange, which is the number 3. So you directly convert that last one into zeros. So 4, 7, 3 zeros. So 47K ohms is what this is, 47,000 ohms. Now, a lot of these are body and dots, so we're just doing a dot on the body. You have an entire line drawn around it. It's the same type of thing. Alright, so let's test this one. This is the same type right here. So we're just going to cross this one here. As you can see, that's a long distance away from 47K. It's 55K. It's replaced. Same value. Yeah, 61K. So this is very loud. This one here was supposed to be 500. 560 ohms was supposed to be replaced. This one here is supposed to be 47 kilos, it should be close to something close. If you lower the screen, you get certain stages, you also lower the sensitivity of the receiver. And of course, you have resistors like this in the line area that are a lot higher now. Let's put that that everyone's going to change as well. Because there's a price of resistor across that resistor. Of course, again, the receiver sensitivity is going to be affected, especially if it's power the screens, the radio receiver, or say it's in line with a transformer that runs to a whole back includes something like that. Maybe one for one across this, and that's a 560 resistor. Here's the bottom side on the chassis. We have all of these fixed components, as you can see here. We have all of these devices, power burning capacitors, and all burning caps, and all of these components. You can see the resistors that are changed. This is on high, 47 kilos to here. This is 560 here. All the caps, there are lots of little caps and components, so they're all over the place. These are the caps that are across that 10K filter and audio section. More of these under here at the Bermuda tar filter transformer, tar crude transformer. Just the amount of work that's on the bottom side of this thing is very incredible. The main depth capacitor that used to be here is now replaced by these two components right here. I'm going to actually show you how bad that cap is. It's over here. You're going to visit that here in just a little bit. This is the depth cap. So it is very peaky. So these are X1, Y2 rated caps across the line there. I love the original line cord in because it's flawless. The original cloth cord is soft. It's absolutely flawless. Now this line cord is not to be confused with a curtain burner. This is not a curtain burner line cord. This is just a solid wire. You'll hear the term curtain burner. What that is a resistor line cord. So the actual line cord of the radio receiver itself is a resistor. And that was used in some of the early series sets to create a drop across the line cord so that the performance radio gets the correct supply. So again, those resistor line cords are known as curtain burners. Now they look a lot like this, but this is a standard line cord. It's just a standard copper wire. So no problems there. And again, it's flawless. The line is not naked. It looks completely fine. It's soft, it's wide, it's flexible. It's kind of nice to look at on it because again, it just maintains the original view of the radio on its side. It's pretty good. What I was going to tell you about this, these are these main cancer caps here that are just absolutely fine. They're the bottom of it. See that? Here in Canada right there. Those ones seem to be okay. Now mind you, a lot of waxes for the Canada as well. Of course, again, it's in Canada. These things are just boring. So these are really, really good. So the micas are okay. The paper and foil caps are the exact opposite. Those are very, very good. So lots of work going on here. The filter caps that are right here have been replaced by these modern Ruby coated capacitors. Very, very good capacitors. This is the resistor on the back that often fails. That resistor I was talking about that they don't give you any ratings for in the parts list or anything. So this is here. As you can see, I've actually drawn in some bigger ratings. This is a good ratings there. You can see I've actually just written down or drawn in the resistor where they go. Put their values there. Right on the script. You can see on the back side here, I've taken a piece of that. Basically, it's thermally conductive silicon that's designed for putting the semiconductors against heat sinks and transferring the heat to the heat sink. So it's resistive, and I've also put that underneath here. What happens is, over time, this plastic body of this resistor, or the compound that they're using, it shrinks up a little bit, and the bracket gets loose. So by putting this underneath here, it acts as almost like a cushion, and in the tight spots, it's very tight, and it also can expand into the areas that aren't so incredibly tight. So it makes nice thermal conductivity all the way across the entire resistor body to the back, and it keeps everything very separate. So that's just something that I want to do. And there's no heat sink compound or anything. It's just that piece of heat transfer silicon underneath here, and it's tight. It just makes it really tight. So keep that in very good condition. If this isn't bad, and you can replace all the caps, the chances are this will not go bad. It's just the capacitors that destroy these things. Sometimes I've seen people reading these things. And what happens a lot of the time too, they get so hot in one area that it chars the area, and that area becomes conductive. And the actual resistor from the B+ section, it makes somewhat of its own resistor because the material is locked up to the chassis, and it just makes everything all that much worse. So burn holes and everything like that. So this is a nice, very clean managed chassis as well. So it's just a win-win situation doing these resistors here. That is pretty much it. That's all that's done here. And on the bottom side, anyway, you haven't put the band switches yet. I'm just going to spray the switches with contact here, and I will do that. And the next step after that is to So there's a little index here as well, so we put it back here and get that here, so the index lines up with that. it's loud because I wasn't speaking on doing this. Let's see what happens. Maybe you're first or not. So on there. 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 Off that. Okay. So now this. That. 1.55. Not good. It needs to get changed. So 1,500,000 yards. So that's already halfway to the make. So that needs to go. So there you go. So if you ever have a microphone that's not as sensitive as it should be, definitely want to change its resistor. And as you can see, its resistor needs to get changed. Again, it's halfway to put a microphone in. So 1.5 millimeters is way too high. It should be in some cases just a little bit lower. So I'll change that out. And I'll go grab a speaker. I'll flip the chassis over. Some clear sleeves in here. All right. Make sure that's what you think's going to happen. You think this is going to work? Have some magic smoke. So before I did anything here, I put two knobs on this two controls here that are a little bit hard to carry. This one here is the IF band, and the one who already comes over to move those two slugs on down inside there. It does get a little bit rough to carry. Of course, this one here is band switch, and has the ratcheting effects. So put two jump knobs over here, and the other two is just this thing. I stuffed the eyeball back in the top here, so hopefully you're not going to stay in there. It's just like this one springs loosely, and hopefully it's this one. I might have to twist it around the walls, shadow walls. Okay, so this is plugged in my isolation transformer, currently very active one, and I'm ready to go. So I just want to make sure the volume is down. It is, as you can see here. The volume goes up and down. Make sure this is down before anything happens. Okay, there we go. It's on. It's on. The switch is on. That. So we can warm up the hot. I see it running low. It's inside, so it does have to be crossed over back here working. Just watching everything because that's a very bright thing. So keep turning it around. Oh, it looks like it's something supposed to be going. So if I try to let it fix here, we'll watch out some of that and see if I can eye a little bit better. Come down here, so it's not totally looking to these are the radio. Okay, I can already hear radio stations on that. So this is the range it picks up. Not much eye action happening here. Lots of bass. So that's what the IF bandwidth. Down the bottom here. Let's find something here. So what I'll do is I'll turn this up here. Actually, a lot of trouble come in. Wow, so it's really, really sensitive. Not bad, and it sounds so full. Amazing. The bass, this is rather speaker down. So 6L6 is a good speaker, very nice. Just trying to the band. Let's see this one here. Just get a switch with a bulb. All that way. So let's see if we have the WAVAPI at 5 megs. Look at that. There's no RF limiter or oscillator in here. That's the time signal is 5. So this band goes down 1%, so I can get a 2.5 in here as well. Let's see if this is 2.5. And now you think you're slick. It's a slick radio. Let's see if you come in at 2.5. Okay, so here it is, 2.5. Okay, this is ridiculous. This thing hasn't even been running. That's 2.5 megahertz time signal. Okay, so this is a 5.16 experience, so let's see if you can hear me at 10. This is 10 right here. So chances are you can hear my own oscillator because I have a 10 megahertz standard in here. So you'll probably hear that. There it is. Wow. 15? That portion of the band is out right now. Okay, so let's go down to, yes, the looping band. It's a beacon right there. Wow. Well, the oscillator's pretty close. The oscillator itself on this thing is pretty close. So obviously that person is past his good I'm sure he's doing a good job. Yeah, I would be very interested in the IF and what's going on with it because I've noticed that our IF bandwidth is narrowing. It takes a lot to cause the eye to flop in order to the full reflection. So the eye can stay in the 2 hours. So it doesn't seem to do that with the bandwidth. Very, very show you how sensitive it should be as well, so that it can cause this to happen. Now, this has two IF amplifiers, right? Three IF transformers. The reason that it has the extra IF transformers is because when we broaden the IF bandwidth, of course, we lose sensitivity. Well, in this case, the sensitivity is actually up as we broaden the IF bandwidth, so the IF just might be really low too. So I'll get this thing attached to a spectrum analyzer, and now we've seen exactly what nothing to do. These little adjustments here. There's an adjustment here, and an adjustment at the bottom, here, this one here, and here, and there's another IF transformer as well. So these little adjustments here are really twisting. Let's see, actually, just for curiosity's sake, if these are live. Let's see. Here. And let's see if these are live to the case. Sometimes they have the plus on them. Turn this on to here. This one here for a moment. Very carefully. Very carefully. Let's see if I touch the chassis. And then this. No, they're not live on this. Not using this. That's a good thing. I warn people about this a lot. Some radio receivers, the actual adjustments in the live transfer are live at 30 plus on them. So if you have a metal screwdriver, which you can turn these with just a standard metal screwdriver, if you turn these with a standard metal screwdriver, if they were live, you slip and touch the case. If you remember the game Operation, something like that. So this is one of the things that showing the case and you can damage the IF transformers. So you got to be careful around this. These here are live, so it's kind of nice. Putting a screwdriver is not going to be too good. Now, using a metal screwdriver in all cases is not possible, especially whenever you're dealing with powdered iron slugs. These are just capacitors, obviously are attached into the chassis or whatever. So the magnetism of the screwdriver is not going to affect these. Now, a lot of the times, again, if you're going to be adjusting these things, then you can use a metal screwdriver with capacitors as long as it's insulated and you know it's not live. It's the better thing to do because if you break your two modules in this, these are just big screws screwed into the capacitor here. If I had one of these caps in there, I would show you this stuff. Threaded screw that tightens some points together. So I'm going to count here. Some long tubes will get absolutely destroyed if you try to twist these because normally these are very tight. So again, it's all about balance. Use a normal insulated screwdriver where possible, and then use the other two modules for like they're actually moving and dealing with powder and slugs and things like that. For those of you that are interested in how I attach my spectrum analyzer to a radio receiver or to a sweep of the IF section, this is also valid if you want to attach just a standard sweep up to the slug using a source. This is the way you can do it. So first of all, you can see that we have a modulator here, which is just another name for an extra tube, and we have two input grids on this tube. Now, normally, when a tube something like this is drawn, we have a little cap on the side. But they haven't done that on the schematic for all of these tubes that have caps. So what I've done is I've just drawn it in. So the RF runs fuse RF these coils here, and then up in this line has the cap, and that's the line that I'm going to be feeding a signal from the tracking generator of my spectrum analyzer. So there's a signal that comes out of my spectrum analyzer. So the spectrum analyzer is running to the input line here. That's what I say. So the tracking generator puts a signal onto this line, and I want to put that signal into here. Now I'm going to leave the oscillator running while I'm doing this analysis, and I'm also going to lightly cover my spectrum analyzer into the circuit. So when I'm attaching the signal into this grid line here, I'm not going to directly couple the output right to the cap. I'm going to clip the signal to the insulation of the wire running to the cap, and I'm going to very lightly capacitively couple into that grid. Now, the trick or the key to a successful alignment is to make sure that your test equipment remains invisible to the device on your test. If, for any way, shape, or form, you heavily couple into a very sensitive tube like this or section like this, what you're going to do is you're going to drag your own alignment with the test equipment. And what you'll find yourself doing is you're going to align the IF section and you're going to compensate for the mistake of heavy coupling. You definitely don't want to do that. That is the difference between a good and a bad IF alignment. Now, the trick to the whole thing is that when you're doing this, if you heavily couple in and you, say, compensate for opportunities on IF transformers, when you take your test equipment off, you won't know that you heavily coupled. And the moment that you disconnect your test equipment from this, your IF alignment changes. Because the capacitance and inductance added by your spectrum analyzer when you couple them in is now removed, and that changes the way the IF looks. So very important to remember, whenever you're dealing with an IF section, anything that's as sensitive as this, especially this line right here, you need to extremely lightly couple it in. Now, what I've done is I've created some boxes here. I've released this on YouTube. I do this under spectrum analyzer protection device. So you can find this video, so you see how it's done. It's right here. It's released on YouTube. At any rate, my spectrum analyzer uses these boxes in line with the input and output. So output of my spectrum analyzer will be the tracking generator, input of my spectrum analyzer will be 1 mega, input of 3585B. So what this does is this protects the input. This one here protects the input of the spectrum analyzer. So what happens is there's a limited amount of units of diodes and a whole bunch of capacitors in here that allow me to effectively keep everything flat during the IF frequency. So boxes are flat within the IF range, and it is a very tight range that these are flat. That it allows me to protect the front end of my analyzer. So if I was to say, for example, accidentally touch this to some high voltage, I'm not going to take out the front end of the spectrum analyzer. If you burn out the front end of a spectrum analyzer, it's not like burning out the front end of an oscilloscope. If you burn out the front end of a spectrum analyzer, you have a very bad day. So you don't want to do that. So I'm very, very cautious about the inputs and the tracking generator output on this one. is that attaches to the spectrum output and the tracking generators. This is just as 50 volts and it's exactly the same as this. So it just protects the inputs and the outputs, and it's also an attenuation network here so that it can properly tune these stages. Now these boxes are purpose-driven, purpose-built, and again, you can check out how I built these things right here on YouTube. Just look under my list of videos. Now I haven't released the circuit boards or anything at this point yet. I guess I should, because I get asked for this all the time today about putting these things out. So I'm going to do that. So I'll probably add the files to Patreon as well, so if you want to build these things yourself, you can put some of these things together. So what I do, again, is I clip the signal just in the insulation of the wire that goes to the cap, and then of course the top just attaches to the chassis, and that feeds signal integrated. Alright, and then what will happen is by the time it gets through the live amplifier into this stage right here, this is where I pick the signal back out, and this goes back to the input of the spectrum output. Now this goes to the 1 mega input of my 3585B, and I'm clipping it directly to the insulation, again, on the detector right here. This is a relatively high impedance point in this radio receiver, and that is very easy to drag. So again, with the isolation and attenuation of this box right here, this is actually the box that will be attached to it. I will just clip this right to the insulation and this will clip right to the chassis, and that will pick up the signal and allow me to align this without dragging the cable. That will give you the best alignment possible. So I'll get this all hooked up, and we'll take a look at the spectrum analyzer screen and see how close or how far off the alignment actually is. Alright, let's see where the IF is in this radio receiver. Let's see if it's close or if it's in outer space. So the center frequency of the IF in this radio receiver is 465 kilohertz. Since this is a high fidelity radio receiver, I'm going to want to span about 20 kilohertz. I want to see 20 kilohertz worth of width. So that means that if the center frequency is at 465 kilohertz, my start frequency is going to have to be 10 down from that, which just happens to be 455 kilohertz. My stop frequency is going to need to be 10 up from 465, so 475 kilohertz. So we'll set that up right here. So start frequency will be 455 kilohertz. The stop frequency will be 475 kilohertz, and that makes the center frequency at 465. So I'll just leave everything where it is right now, and turn on the radio receiver and see what happens. I'll have to make some other adjustments here. Let's just see what will happen. I'm also going to put this to 1 mega input. That's what I'm on right now. There we go. Well, already I can see that. So if I move the marker around, if I move that around, you can see this is the here. That's where the center of the IF is right now. 470 kilohertz. That's pretty cool. So what I'll do is I will adjust the computer vision to 10 to so I'll probably down to say 5 just to start off. Vision 5, that looks a little bit better. Now, in order to find out where this actually is, and get as close as we can, what I'll do is I'll just press the signal track for a second, and I'll bump everything to the center of the screen, and then of course we'll keep the span the same. So just go signal track, and I'll shut that down. So there we go. The center frequency is right dead on 470 kilohertz. Look at that right there. So it's 5 kilohertz on it perfectly. So that is way off. So what I'm going to do now is I'll adjust the fidelity control on the front of the radio receiver, and that should expand so you can see this wider out. This is on the narrowest setting there. Whenever the IF adjustments are done, that needs to be done on the narrowest setting. And then once the IF is cleaned up and everything's done, you can kind of critique it on the widest setting to make sure everything just looks good and flows properly. So what I'll do is I will widen this up. So I'm moving the fidelity control right now, and I can feel that little detect just starting to hit the camera right now. So I keep turning. And as you can see, I'm getting that gain. I'll keep turning this. Let's just stop this right about here. So it stops hunting. I'll zoom on into the screen, and that'll give you a better idea of what's going on. There's some close. Hard to check the camera. Let's adjust the focus here. And there we go. So that's why the setting is holding messed up. So what I'll do here is I will narrow this up again. As you can see, it's shifting. So you see the peak is right in the center right there. Now notice that, as I showed you earlier, when I narrow the eye band, the eye isn't working as well. Okay, so this is the narrowness. Now you can see as I'm widening things up, you see how that is rising on the screen? It's going up right now. As that's rising, what's happening is the IF section is becoming more sensitive. You can see that amplitude is coming up. Now as I get to the top, this is about the peak. It's about 3/4 of the fidelity control. So now if I keep going, you can see that it comes down again at its widest setting. That's at its widest setting right there. So you can see this pretty wide. So again, I'll turn the fidelity control back down here so it narrows things up. You can actually see the peak is moving off centrally as well. And then as I bring it back, you see the peak, it kind of scoots towards the center of the screen, and it gets to about the center right there. But you can really see the gain function. That's why the eye isn't working very well. So narrowest, you can see keep in mind this is 5 dB per position, right? So this is, if you want to see that, here, look at this, 4.26. Right? Well, look at how much that's coming up. Right? So you can be about 29 millivolts from that, and that's from just coupling in, on the insulation. So we're down to 4, and we can get all the way up inside and the back of the radio, which makes this extremely loud. Now, not only that, the experimental resolution is sitting right in front of the radio receiver right now. So what I'm going to do is I'm going to make an entire, I should probably make an entire series of two radio receivers using IF sections, and I'll have to create some other brackets for the big cameras and go through that. The entire tune procedure. Unfortunately, in order for me to completely tune this up, I'm going to need to use a camera having to grade out of the way and have to move the radio chassis around in circles in order to adjust this thing. It's just the way they're setting it up. Some of them are on the rear, the tubes are this. Move everything around. Okay, so here we go. I'm going to move that bottom capacitor. You can see how moving Dan around, and now you can see I'm actually shifting the center. So what I want to do first of all is tune for the maximum at 465. So if I move this here, it actually shifted in the right direction. So right about there, so I'll move that marker about 468 now. You can see how much that shifted. So I'll move the capacitor to the top side on that. And let's see what happens when I do that. This one's almost behind the dial glass. This is a, so this is this part. Look at the amplitude coming up. So right now, I'm doing this. You can see the rising and swinging. That sensitivity, that's receiver sensitivity you see happening right there. Lots of sensitivity added just by holding this around. So right about there is its maximum sensitivity at about 468. So you can see, just by tuning those two capacitors, how much this is already improved. We've actually shifted this closer to where it's supposed to be at 465, and the sensitivity has come right up just by tuning two of those capacitors, just two of them. And there's another two transformers, so that's four more of these that I get to tune when I keep bringing this up. So it's way up. You can see that it's absolutely way up. So when this is done, the eye should work very good, and I should get a very nice even spread on the IF when I'm done. So chances are I'm probably going to have a stage curve effect, so a double hump kind of happening on here. And once I've got this all perfected, I will come back and show you what I've done and explain it. To give you an idea of usually how long it takes to do an alignment like this, you're looking at in order to perfect everything to make it look as even, to get the best results possible. It usually takes me about an hour or an hour and a half to do this. So that's just moving back and forth between capacitors and just making sure that everything is right where it should be. And of course, you want to do it just as good when you're widening things up like this. You see, it doesn't look too bad there. You can see the double hump right here, right? But that's just, this normal movement of the fidelity control. That's the end of the fidelity control. Okay? So you can see that it's starting to look a little bit more like it should. That's just by tuning those two capacitors. See the stage curve effect that I'm popping here? So again, when all of this done, I'll show you exactly how this should look. And we'll be on to the oscillator antenna section too as well. Tuning the IF section in the Scarlet Carlson took about an hour and a half, and that is an hour and a half of moving around these 6 capacitors and those 3 IF transformers. Now, I have to tell you that getting the IF to work the way that you see here on the screen without using visual means would be absolutely impossible with this receiver. I'm telling you, if I look at one of those variable capacitors out of the corner of my eye, this pattern that you see on the screen will change dramatically. That's really how sensitive it is. It's so sensitive, in fact, these radio receivers sounded fantastic when you rolled off the factory floor, I'm absolutely sure. But the moment that somebody changed one of those IF tubes or even the detector tube, this pattern would just change. You wouldn't have that same quality of sound that you would have had from this thing from the factory. Give me an example of that. So you'll see that the center of the screen is exactly at 465 kilohertz. Now when I'm working with it, we're blocking up the IF bandwidth, and you're going to start to see that stage curve effect. Now the whole trick of making these IF alignments work the way it should is to keep that double hump falling and rising evenly. So the stage curve effect, those 2 bumps are missing on each side, they need to fall and rise evenly as you're moving around the variable IF bandwidth. So as those 2 slugs are moving up and down inside those 2 IF transformers, they need to basically work with each other correctly in order to get the sound. Alright, so I'll give you an example here. Alright, so I'm coming right to where this detail is now touching the cam where it's going to start moving those slugs. So here we go. Keep in mind that this is now at 2 dB per division. I had it at 5 dB before, but at 2 dB it's, you can see much more deeply. Okay? So now you can see how it's widening up. Okay? Now you can see how I'm getting the stage curve effect. You see how we have those 2 bumps on each side. You see how they're forming evenly? That is a very difficult task to achieve because we get a bump on one side and we maintain a flat mark on the other side. So here we go. I'll move this down to its widest IF bandwidth, and as you can see, they fall evenly, and as I raise this, they rise evenly and they form the perfect bell curve in the center, and then as we come to our narrowest bandwidth, you can see the amplitude dropping just a little bit. Now that's absolutely normal. Keep in mind we're also dealing with 2 dB per division, so what you're seeing is very, very minuscule. So making this happen just like you see right here, and then falling evenly like this, is the result of about an hour and a half of tuning. That's going back and forth between all of those capacitors and making sure that I maintain the 465 center, and then I have those 2 bumps forming on each side. Now this is the best it's going to get. You'll see right at the center, right at the very center of the dip. So right at the very center, you can see the marker moving around there. and put this together. So what I'll do is I'll give you an example. If I just I'm telling you, touch the values, if I just push all those capacitors, watch what happens to the pattern. Ready? Let's go over here. Capacitor. Just press it. Yeah. So if I just tell this out a hair's width, we'll say 80. Look at that pattern. The pattern is immediately destroyed. We're talking moving that hair's width, right? Alright, so just the IF here so you can see what's happening. So you can see it forms somewhat even at the center of the back. It comes back down. But then once we start to widen it up, we get one bump that's way off to one side. So our peak sensitivity will be off to one side of the IF. And as you can see, that's just really no space right now. That's by moving just one of those 6 capacitors. So that hair's width, so you can get an idea of how long it took to actually figure out how to make everything track. So as I say, doing this by just a peaking method or using a BTM or something like that, impossible. Absolutely impossible to get what this is doing over here. So this radio receiver with that IF that you see there will sound fantastic. It will sound like an FM radio when it's quiet. So what I'll do here is, since we're at our narrowest position here, what I'll do is let's calculate to see how wide the IF actually is, just to make sure that that's at its narrowest point. So we'll adjust the reference volts here and bring this up to the top line. So we'll go here. That's pretty close. So if we go 24.5, that's 21. So let's see, say 23.5, let's try that. 25, it's a little bit too hard, let's go 24. It's very close to the top. Okay, so what I'll do is I'll turn on the display line, and I'll move the display line right up to the top. So if you look here, you'll see that this comes to 0, will be right top line, okay? So since this is locked, we're going to move the box down, these are down 3 boxes, alright? So I'll move this down 3 boxes. And as you can see, right minus 60 right here, this is where they normally measure the IF width. Okay, so I'll go back to the marker. I'll use the marker off to one side, but right at that line. Okay, now we're at 467.08. Alright, so I'll get the calculator there. So 467.08, and then we go take it away, so go to the other side now. 462.92. 462.92. So we're dealing with 4.16 kilohertz of bandwidth. Not bad. That's pretty narrow. It's very useful for communications quality stuff. So it's going to allow us to really narrow down frequencies that have other frequencies very close to them. So we can really just get rid of the adjacent frequency noise. So it's pretty decent. Not too bad. That's at 6 now. Usually I have to move down a little bit. 6 is actually kind of generous. But we'll just stick with the 6 because that's usually what these numbers are. So 4.16 kilohertz wide in the narrowest position. So now let's go to the widest position and see what happens here. So I can probably bring it down to some reference volts. Down here, and I'll bring this back up so we can adjust this here in a moment. Okay, so pop that over here. So let's try 16. 16. That's great. That's close enough. Alright, so we're still at the 16 down point. This is display line here. Still at the 16 down. So I go to display line. That's 2 meters long. That is long again. 3 boxes down. 2 dB per box. Alright, so what I'll do is either roll the marker back over here. Alright. Pump this one. This one. Back to marker. So right there, we're at 475.6. 475.6. Okay, other side now. 454.56. So 454. So 454.56. Alright, take away 454.56 equals 21.04 kilohertz wide. Pretty fantastic section. So we divided by 2 equals 10.52. So this is 520 cycles above their audio cutoff filter that they designed on the other side of the chassis. Can you see stronger parts of the network? to each side of the center. This rate of receiver sound absolutely fantastic. So there you have it. That's how the IF should look in one of these radio receivers. Keep in mind, if you're ever going to line something like this, you need to make sure all these things fall and rise at the same time. You want to maintain symmetry as close as you can to their design. And again, you can see that the center is out just a touch. It's in the perks here. So we're using the marker here. Technically, that would probably be the lower there. You know, so not a big deal. Not a big deal at all. It's so close. For IF transformers design in the 30s, this is ridiculously fantastic. So anyways, let's get on to the other portions of the line. The antenna and RF1 is radio receiver. Not only with the oscillator adjustment, because the frequencies, as displayed earlier, are spot on. And it's, yeah, this thing's so close. I've actually never come across a receiver that is this close right now to doing the actual line oscillator. So these are the oscillator adjustments here that don't need to be touched. This is the RF adjustment here. This is the RF right there. This is the RF adjustment. It's in that box there. It's the RF adjustment. So and this is the antenna adjustment right here. So this right here, this one right here, for the broadcast band. So I have my signal generator set to 1.5 megahertz. And I'm at 100 microvolts, so I just move the dial to 1.5 megahertz here. That's so ridiculously close, isn't it? It's spot on 1500. And that's with the IF width narrows. It's right on the line. Again, I've never come across a receiver that's ever been bench that's so in tune that way. It's actually kind of surprising. So now that the IF section is done, we can use the I itself as a tuning point. So I'll just turn this off frequency here again. I'll show you the IS function correctly. I'll show you some of the light from here. Now the capacitor that's in the circuit here, the time constant for this is it's slower than I was tempted to modify that in the design, let this thing respond a little quicker, but it's okay. Okay, so what I'm going to do is adjust the antenna section here and just tune for a beat. So I want this to come as close together as possible. And I have a feeling this is probably spot on. Okay, so let's see what we're at. Chassis, and this is right up here. This one's this like so. And this one here. So we need to also get locked on with here. Again, can we ask if there's any for maximum closure? Right there. It's really spot on. Now if I was to push the oscillator adjustment right here, it would just tune this thing to frequency. That adjusts the dial tracking. So I definitely want to be touching that because when I see this thing spot on, it's spot on. I2 here is looking okay. I might be a little bit tired because I might just grab another I2 here. So that's great. It doesn't seem as sensitive as it should be. So give me a second. Just unplug the I2. Another one here across the flat. Here's a brand new one. This is a JN1 joint number 8065. So this is very nice too here. Plug that in and see if that's any better. This is brand new, so I think it's pretty good. Some of the waves, so to say. Closer together. Just move this off frequency here. That's definitely more sensitive. Yeah, it's quite a bit greater as well. So I'm going to leave this one here. It's very cool. Nice IQ there. So now what I'll do is like exactly the other bands do the exact same thing. Basically, we rotate the band switch here, like that, and then we can expand and turn it down. So I'll start at the bottom, I'll start with band X, and that's these adjustments here in these cans here, so I'll show this to you. Looks like they're falling off the bench. It keeps let's do it. And then I just have the oscillator tuner here. So very simple language. Everything, as I say, the whole oscillator section here seems to be raised on frequency. So the first thing is here last, you can job in the RF and the antenna and the oscillator section that wow, that RF is outer space. So everything good except the IF is aligned with by the previous technician. Another point that's radio system that has been most likely detuned over time and never been tuned properly is this 10 kilohertz audio cutoff. So the little filter network down here is in the capacitor across it that's designed to cut off the audio after 10 kilohertz. So this is between the last audio amplifier and the grids of the 6L6s. Now there are no instructions on how to adjust this in the 100% use. That's something that was done at the factory. I guess they just expected you to leave it alone. I would imagine way back when, Stromberg Carlson had a swoop set for the audio section in this as well. So I'm going to use my Stanford Research SR7E to swoop the audio section and I will make that adjustment. So I have the sweep set from 8 kilohertz to 12 kilohertz, and that should get us within the range of this adjustment. And we should be looking for a dip or null around 10 kilohertz. So I got the marker set 10.02 kilohertz. The reason it's sitting at 0.02 is just because I have the points I have here. If I opted up the points of sweep slower, and slower sweep is pretty here, let's just leave it here. And put search results. Turn on the radio receiver. The tube's still on. The analyzer is toggle use. Pick up what we see here. Let's see what this thing's saying. This is something that's right here. So you can see the dip of the null is actually quite early. So let's see what it's saying. It's sitting around 8.5 kilohertz. That's okay. It's supposed to be at 10. So I need to move that dip over to this line over here. So what I'm going to do is insert the screwdriver into that adjustment that I just showed you. And give it a twist. That's the way. Go that way. Just try the other direction. Now I have to wait for the analyzer to catch up because it's a slow sweep. We're going in the right direction. That is a good sign. So there's quite a bit of adjustment going here. So that's good. Just go there. I passed it. So far connection. So you can see I'm completely past it. So I'm back to control button right here. And that dip is right over that line. So every time the sweep goes past, you just go there. Let's see, it goes right here. A bit more. Just moving control there. I think that's it right there. That's looking pretty close. Let's up the number of points here. Let's check that one here. Right here. It looks like it's spot on. That is a slow sweep. That was right in the middle. Ribbons all put back together. Let's cruise around broadcast band and see how this thing sounds. So hopefully Mike will pick this up. I have it pointing towards me, so it is a really full sounding radio. So some volume here. You can see I'm turning the volume up. It moves out of the scale up over there. It has this little red dot on one side, which seems to be almost the perfect volume all the time. That's very interesting. Okay, here we go. Incredibly full sounding radio. That's like the most fidelity. Stations absolutely everywhere. The radio itself turned out very nice. I'll give you a view in front of the radio here. It's a nice gold leaf and the brewer there. They turned out really, really nice. Cleaned up the wood just a little bit. Basically, we didn't need too much. Does that work out well? Let's just try the band here. Let's see. This is a beacon band. This is aircraft beacons down here. What I can do is zoom in just a little bit more. Actually, no, this lens is going to allow me to zoom. So let's just give this a shot. Let's go. Here's some volume here. Here. Right down the bottom, not a whole lot down around 145 kilocycles. That's way down the bottom. That's way below the IF frequency of this receiver. So it stops about 360. This is 370 right here. 360 was the last. That's far enough away from the IF. So that, 360. Just 360 there. The last 370 right there. So yeah, it's way down. Now they have police right here, but I think that's for the next band up way back when. So let's just a bit and let's see if we can find something a better example of how I feel it sounds on this. The problem is that you need music to do that. That we know how that works on YouTube. So let's see here. I can find just a station that has some pretty clear talking. it sounds like the person is sitting right in front of you. It's just incredible. So next range up here, and let's see, these ranges, the higher you get frequency at this time of evening, it gets really quiet. I'll see if I can find the WWV, I should say. The VB is down to 60 milliseconds. So the WWV should be at 2.5 at this time. There it is. I don't know if you see the action of the eye. It's kind of blown out here. Let's see if I do this. All right. Now, if you remember the IF curve, way back when we were doing the alignment, you get a certain way through the fidelity, it comes to a peak and then it comes back down again. You can really see that with the fidelity control, even with just the noise. So what I'll do is I'll bring this to the start. Okay, so this is the start of where the cam is just touching the slug. Now, as I increase the fidelity control, you'll see just from noise, the actual eye will close. So that's its peak right about there, and then as I go to full fidelity, it opens back up again. Just a little bit. Right about there is full. There, I don't know if you can see that. Very little change, right? But at any rate, that shows you that, you know, this is following what we've done in the IF. So very interesting. It sounds the best right about there, about 3/4 of the way. So anyways, let's try and let's go to the other one. It's at 5 megahertz is the other time signal. That's very strong. So I don't know if you can see that. That's going to be focused there. It's pretty much closed. So I'll go off frequency. Lots of noise. I have this hooked up to a really large antenna, so this wants to receive lots of stuff at this time of the evening here. And this band is pretty active. Very short wave broadcasting here. This is pretty much between 80 meter ham band and above. This is all quiet. Oh, there's some sideband in the 80 meter band. Somebody was there a moment ago. And the upper band will be just pretty much quiet at this time. See if we can see my oscillator, 10 megahertz here again. There it is. So that's my own standard here. This comes to life during the day, and this year will actually just bring it back to full brightness here. So this comes to life during the day at the top band here. This is kind of middle to end of the day, and of course this is the beacon band here, which is active most of the time with local beacons. So all in all, so here it's down here, and this here. So all in all, the radio itself is it's working just absolutely fantastic. Out of most of the radio receivers that I have restored, I honestly have to say the Stronger Carlson is probably the most enjoyable to use, really. The fidelity control, as you heard, is just makes AM listening fantastic. Now, you can't really use the fidelity control if they're station on station because they're close together because the IF just goes so wide that you're kind of into the next frequency. So when stations are piled up, you have to have this narrow. It really does narrow the frequencies quite well when they're very close together. So that very low IF really does help. Tons of audio driving power. It gets quite uncomfortable after that dot. This is the dot right here. As you can see, I'm kind of raising my voice. After that, it gets absolutely crazy. So those sixes are driving speaker. The difference of having that speaker sitting in this cabinet with the acoustic labyrinth behind it is somewhat amazing. The bass frequencies, the lows that come out of this radio receiver are absolutely astounding. The lows are just, even describe it. I was listening to some country music and just all sorts of different things on the AM band here earlier, just trying to find as much different music programming as I can. And it sounds like it really does. The bass is just rumbles the place. If you have a chance to get one of these radio receivers, if you find one of these Stronger Carlson 145s, I strongly suggest if the pricing is right, pick it up and put the time into it to restore it. If you like listening to AM and these radio receivers, this radio is nothing short of fantastic. It really is.
I'm thinking of another husband or wife, because I use the wife because I think it leans that direction or something, where she doesn't feel connected in her emotionally, spiritually, maybe even physically. So she's drawn into this conversation. Okay, there's some things I need to do. Maybe it's not husband.
Here's another example of how this sounds with the microphone more optimal places for that. The only way to really appreciate factory device, it is actually showing the parts that have circles on the chassis. This is the thing, it's flipped in on the hole here on the bottom of the chassis, so it runs through the side of the chassis and bend this tab up. Original device, so let's see how bad this actually is. So we want to understand around the function of this particular device here. So AC line for decoupler and all sorts of things to do with RF and ELI and all sorts of things. I'll get into the exact description of what these capacitors do. Their functions vary within different devices actually, but you'll see the same kind of setup. Sometimes you'll see one, sometimes you'll see two, sometimes you won't see any at all. It just depends on the actual device itself. That capacitor in this case, it's an actual radio receiver, so it's doing multiple things. Anyway, so what happens is this thing ends up failing, so they short. And what they do, one side will short, and both sides short, they take fuse. But if one side short, what it does is it take one side of the line and put it directly on the chassis. So it's a very safe situation. That'll cause some issues. There's replacements to these capacitors are these ones right here. So this is known as an X1, Y2 rated capacitor, all sorts of safety ratings. And these are designed to fail in a safe manner. We'll get into the failure points of these capacitors and get too deep into the caps here. But at any rate, this should be replaced with a very safe device. If you're storing out radio receivers that have these caps, it's an absolute must to get rid of these things. You can overheat these behind, like the previous people have gone through this radio receiver. So you definitely don't want anything like this to go bad. So let's take a look at what's actually going on with this thing here. So this can be directly, the scale rating device can be directly converted into ohms. So basically what this is going to do is it's going to look for the resistor that this thing is trying to turn into. Okay? So this is a very sensitive device. This thing will go up to 40 billion ohms in forecast position to really look for any type of voltage, any type of resistance that we have hiding in these capacitors due to just gradient, moisture, aggression, all sorts of different things. Again, very purposeful device. So the first scale is red. It's a really bad scale. And then the yellow, it starts off as yellow scale, and the second scale works down and becomes green, about 40 billion ohms. 40 billion ohms if you prefer. So let's see how actually bad this thing is. First of all, let's test it. Okay, so this is a brand new capacitor here. So I'll just turn this on. We'll read the resistance on my hands as I'm holding these things. So I'm tapping the test position here. So the first scale is red, as you can see. And when I'm holding this here, I'll bring it up to the yellow scale, to the top of the yellow scale, to the good ones. Okay. And then if I short them together, you'll see that that's a dead short. So that's the start of the scale right there. And then you can be on this little mega and it works its way up to 1 gig. The scale flips and goes from 1 gig to 40 gigahertz. So I'll put this on here. So there it is. Okay. On the test, as you can see, it's comfortably going up to 40 billion ohms and beyond in forecast position. The forecast position on this thing is the most sensitive position there is. And again, if I just touch the birds this very, very lightly, you can see that I'm discharging that cap at 40 billion ohms. So it's reading my body resistance through a vinyl tube. So it's reading the resistance of this here on my entire body and then back to this loop here and the resistance again. Okay, you can see that? Just by lightly holding it. It's a very sensitive device. Again, it's designed purely for obscure issues. So here is the dead cap. Okay, so I'll put the positive loop there. And don't be confused. You can see a chassis brown, so don't be confused by that. This is an alternating current capacitor. Again, because these capacitors are non-electrically polarized. So it's in a shell, and of course it's designed to be approximately the same wire. So polarities flipping around. So let's test these out and see what we get. Should be interesting. Here, actually, please don't touch anything. So as you can see, that's pretty bad. So that's going to be just below 20 megohms. So this next light up will be 20 megohms. Okay, grab this resistor here, just give you an example. Together, these are 20 megohms each way. 20 megohms should be the next light up here. So very bad. So you can read, you would actually have to read this is so bad, you can read that on the standard DMO. This here goes way beyond the standard DMO. So there you go. So that's 20 megohms right across that one. So it's going to be below 20 megohms with this. So if I was to put this across the DMO, it's going to be very close to, I'd say between 10 and 15 megohms. So you can see that this capacitor really bad. Let's test the other one. Test it one here. This is the one that we tested here. Creep up just below 20 megohms. Okay. And let's test this one here. And this one here is open. Oh, no, it isn't. So this one's on the verge of shorting out. This one inside that would have most likely cause very bad issues. You see this thing? It's in a red scale, and it doesn't know what it's doing. So right now, if this was attached to a line cord, it would be inside, it would be shorting, it would be sparking, doing all sorts of things inside there, because it's intermittent. As you can see, it's intermittent red scale. So it's really, really bad. So this would be the side that caused the issues. So now depending on what side you plug this into the wall, okay, remember this is putting more voltage across this is this issue right now. So the line cord that's on this thing isn't polarized, so you can plug it in this way or plug it in this way. So there's a really good chance that you would put the hot side on this and that would have been connected to the chassis. As you can see inside, it's intermittent. It's basically this would be, you can say, sparkling inside right now or sizzling inside there right now. And I can almost guarantee if this was plugged in the next time this was plugged in, that would become a dead short. So it would have attached the line to the chassis, so anything like that, that was caught just in time. This other side here seems to be pretty constant. This one here doesn't do the same thing, so here's just showing fixed resistance. So this is that other side would have been an extremely dangerous side. So prices are right there. So this thing is working, this thing in. And that was on the verge of happening. The chassis was maybe or something was on the verge of being run. Who knows if these were actually short of taking that fuse out. It's hard on the power switch, it's hard on all sorts of things. So definite crisis averted right there. And if you're interested in building these things, again, this is taking build plans along with many other of my creations out there. Definitely check it out. You can join the videos, you can go about it, big thumbs up, and you know, videos like this can be in the future. We'll be taking a look at vacuum tubing, solid state electronic analysis online. So if you haven't subscribed, that would be a good time to do that as well. If you're interested in taking electronics knowledge to the next level and learning electronics in a very different and effective way, and being access to many of the personal electronic inventions and designs, you're definitely going to want to check out my ongoing electronics course on Patreon. I'll put just below the video's description on the show more tab, and I'll also pin the link at the top of the comment section, so you can click on the link and it'll take you right there. Alright, until next time, take care. Bye for now. Hi there, and welcome to another episode of Mr. Carlson's Lab. Today we're going to troubleshoot, repair, and modify a signal tracer from YAVAPI. Signal tracers are great tools to have on the bench, and in many cases they can even replace an oscilloscope in many troubleshooting procedures. Oscilloscopes allow you to see what's going on inside the circuitry. Signal tracers allow you to hear what's going on inside the circuitry. So it's just another device on the bench to bring you closer to success in your next repair or restoration. Now signal tracers like what I'm going to show you today can be had for really cheap at local auctions or swap meets. And usually, because of age, they're in some state of disrepair. So after some quick repairs, usually they're ready to go. Now in this video, we're going to go a little bit further than that. The line cord is cut off this thing, the case is looking pretty bad, so chances are I'm going to do a pretty extensive repair on this. And as we encounter problems inside this, we're going to repair them. And if the design needs any modification, we're going to modify it as well, and I'll explain exactly my thought process as I'm going through these modifications and repairs. So hopefully these modifications and repairs will pass on some information to you to help you in your next repair or restoration. So we have a lot of territory to cover in this video, and I'm going to share some hints and tips with you about vacuum tubes and some other things along the way through the videos. There's a lot of really neat stuff coming out through this. So let's get started. I'm sitting right beside me at the test bench, so let's take a look at what we're up against. This is a Stark signal tracer, and it looks to be in pretty nice condition. Here's a probe that's missing on the coax. You can see the exposed center conductor here. Aside from the paint that's been ruined by somebody using a permanent marker, a few screws that are missing, it looks to be pretty nice. Now, one word of advice, if you're ever going to try and sell something like this at a swap meet or online or anything like that, don't write the price on the paint with a permanent marker, because when you say permanent, it does not drum off, it goes directly into the paint. Somebody's taking the time to try and take the price off of here because they've polished it or done something to use acetone or lacquer. And what that's done is that's taking the texture right off of the paint itself, so we have kind of a flat look over here, and you can still see the price in the paint. That's permanent. That will never come off. You have to strip the paint to get that off. And this is what I'm going to end up doing with this. This is not going to be a shelf clean. This is going to be a piece of test equipment that we are going to actively use together to troubleshoot other pieces of test equipment, transmitters, whatever we're going to troubleshoot at the time of the bench. So no shelf cleans. This is going to be an active piece of test here, and I want it to fit into the theme of the old-time workbench. So what I'm going to do is get rid of this ugly beige color, and it looks like we paint this in a hammer clean black or something like that. It's going to fit really nicely in the old-time workbench. So you'll notice a lot of older pieces of test gear have this somewhat beigey, nicotine type colored paint on it. And the reason that they did that way back when is because it was really quite common to smoke in the lab. Everybody was smoking way back in the day. So by using a beige colored paint on a case like this, when it did get stained, it kind of just blended in and there was a lot less clean. Hewlett-Packard used a color that was very close to this, very close to what the Stark is used here on this piece as well. So it really is an ugly color, so I'm kind of looking forward to getting rid of this. And the black hammer tone will work better with this white colored face and the black knobs and everything like that. So we'll kind of be in line with everything else here. Probably end up using this grill here by the speaker as well, because this is the same color as this paint. Other than that, it's looking pretty good. So I don't know what's inside this. There could be bricks inside this thing. As I mentioned in all the other videos, as we go through this and repair this, I'm discovering the problems at the same time you're seeing them, so we're repairing this in real time. Now there is hardly any screws in the case. There's one screw back here, there's one missing here, and the line cord is trimmed off the back side as well. So it's obviously in some state of disrepair, maybe they trimmed the line cord off for a reason. So what I'll do is I'll turn this thing around, we'll take a look at the back side, and then what I'm going to do is remove this from the case, take a look at the circuitry on the side, take a look at the design that Stark put together, talk about that a little bit. Here's the back side of it, and as you can see, it's in pretty nice condition. It's a screw missing here. There's also a screw missing on this side here. So it really looks like the screws going together. There's 3 right here. Nice sticker here. It says special inspection series T approved by regular calibration and material. Line cord has been trimmed back here. So line been trimmed here. Find out here soon. So other than that, it's pretty much ready to be taken apart. So let's go ahead and take these 3 screws. Let's see what happens. Just take this out of the case now. So it looks like this is just now. Like that. So just leave this here like so, just for a second. Take a look at this, and what I'll do is I'll just take this off the bench and work around the camera here. So it looks like everything here is intact. Look at how clean that is. Just dust on the chassis. So what I'll do is I'll pull this out of the case and get the case out of the way, and move the camera around, and take a better look at this. Let's look at the design of the Stark ST2 and see what we can learn from what they've done. Now, I can tell you this already, I already see a bunch of flaws on the proportion of this chassis. Design flaws, very basic stuff. So if you want to guess at what the design flaws are, what I'm going to do is move the chassis around slowly, and then when I'm done moving the chassis around, you can pause the video, take a guess at what you think the problems are, and then when you pause the video, I'll tell you what they are, and we'll do the same thing for the bottom portion of the chassis. So you want to get your arrow ready to pause the video. So here we go. I'll move the chassis around, and you take a guess at some of the design issues. Want to get ready to pause the video now if you want to take a guess on what the issues are on the upper portion of the chassis. These are the issues with the upper portion of the chassis in the Stark ST2 signal tracer. So the first thing that tells me that this thing is going to hum all the time. So if I was to pull the tubes out and everything and just plug the unit in, this thing is going to hum. Why is that? If you look at the audio transformer, look at how close this audio transformer is to the power transformer, and they are both situated the same way. These two are going to couple. The magnetic field from this power transformer is going to couple into that audio transformer, and it's just going to make this speaker hum all the time. This is really basic stuff, and I don't know why Stark did that. This transformer should be out of the way of this transformer, and it should be mounted 90 degrees, so to stop that hum, at least bring it down to a very minimal level. The more you load the plus or the filament winding on this, of course that field is going to get stronger, and what's going to do is create more hum in that transformer. The field is going to interfere with this transformer, it's going to increase hum into the speaker, so really the only way to get rid of that hum all in this design is going to shut this off. Now you're saying, well, how do you know this? It's some shielding on and everything like that. Well, when you work with audio design for a long period of time, you get to know that, yeah, they put the shielding on this transformer to probably minimize that effect due to a bad design. It costs a lot of money to put these caps on transformers, so this looks like a patch. So they probably stamped the chassis, put the whole thing together, figured it was going to work, and then realized, oh, there is an incredible amount of hum, so they had to order a transformer with caps with the caps on. That's the reason we've done this. No matter how much capping you put on a transformer like this, when this transformer is open like this, they're pretty much almost touching it. Look at the clearance there. It's very, very small clearance. Right there, you know it's just going to hum and cover. So we're going to try this out here in just a little bit, and we'll slowly go through this thing and repair this together and bring it back to life and see if we can minimize that at all. Really, the only way to fix this design is to take this transformer and move it somewhere else on the chassis in order to get rid of that just basically, I guess you can call it just static hum. It's just going to sit there and hum for no reason. Now, another problem on the upper portion of the chassis is the placement of this audio power tube. Again, we're in the area of the field of this transformer, and it's just basically just stick a finger through there. So what this is telling me now is that the grid, control grid of this tube, might pick up that string magnetic field, and the audio output tube alone may introduce hum into this circuit. So what we're going to do is we're going to pull this audio tube out, and we'll see if that reduces any of the hum at all, and we'll put the audio tube back in, and we'll see the differences. I can tell you already that this is just way too close. This needs to be here. This can be closer to the front. So you see, this is on keeping the cable. So this could be closer to the front. That's how it should have been. It gets the amplification chain closer to the cable where it's coming in and to the VR as well as the need for it to be this front back. So the closer you get to the front, the tighter things are. And then they could have taken this tube and placed it somewhere else in here. Maybe move this transformer over in this area. It would have been a better idea. We could shove all this kind of stuff over. You know, it's silly. This can could have been put right here. Keep the power supply on the other side of the chassis, away from the amplification chain. So there are a whole bunch of design errors in this thing. we're still going to restore the thing, and you see how useful we can make this little signal tracer. But if you wanted to take one of these things and completely make it quiet, honestly, what I would do is put a belt cord on the back of this thing, put the power supply in a separate box. That will alleviate all the problems in this design. So just get this thing out of here. It's too close to everything. It's even this close to the speaker itself. You know, so if you can feel this with things right in the feel here, in the cord inside here as well. There's just so many things. You look at the top side and you see these problems just everywhere. So this tells me that either a young designer put this thing together at start, or somebody was just in a rush and really didn't care. It's hard to say, but the amount of flaws in this design are really incredible. It looks really nice. I have to admit, the way they've laid it out and everything, it looks nice. Nice and compact and everything. But looking nice and working properly are two incredibly different things in the electronics world. So let's take a look at the bottom portion of the chassis now and see what we can do to make that a little bit better and spot some problems there as well. Here's the bottom portion of the chassis. Let's take a look around the bottom portion and see what we can spot. So again, take a look at this just like this, and get ready to pause the video and move this around just a little bit. And you take a guess at what some of the issues are on the bottom side, so that you know when to pause the video. So take a look at it now. The lines that are is this way here. Grab this, a little closer. Start moving around. Being able to pause this at any time. So just a little closer. Chassis of this ST2 signal tracer. So the very first thing that caught my attention is these two connections right here. Take a look at those connections. You can see that there's absolutely no signal. So the wires have been wrapped. These connections are not visible whatsoever. Now keep in mind that this thing went through a special inspection environment. So it's back somewhere. It's a very interesting special inspection. So if there's any current demand on this outlet, this would be very, very noisy. Very noisy connection. So that definitely has to be fixed. The next thing I noticed is they're using half-wave rectification. So you can see two red leads, which are the main test leads. One runs right to the chassis, one goes through the diode, so you can see at this point here. And then there's no filter here. They run it through a 220 ohm resistor, which allows you to drop the voltage, and then runs into this capacitor right here. So there's 3 filter caps in this can. I've yet to discover where to go and what to do. In fact, I'll look for a schematic and look for a schematic to look at that as well. So they should have a filter here alone that's going to make some more problems. We'll experiment with this design here a little bit and see what adding some filters and stuff does to this. We'll go through this piece by piece and try and improve their design to a point. Really, what should be done is maybe we should move around. We should completely redesign, but that's really just ST2. Carl says ST2, so I don't want to change it that much, but we'll make the design a little bit more usable. Another big problem, ceramic disc capacitors in a high gain audio stage is not a good idea because ceramic disc capacitors aren't microphone caps. Ceramic disc capacitors, and you'll hear the tapping quite clearly in the speaker when it's using the monitor what's going on. These should be a type of a poly back in the day when there was paper and foil stuff. That should have been a poly style capacitor or whatever we had going to slow down on that microphonic issue. Sometimes these things are so microphonic that they actually hear the speaker and start feedback loops and start howling on the whistle. So here's the thing with ceramic capacitors. They're great for RF bypass, just general bypass capacitors. These things very rarely fail. So whenever you see these things, whenever you restore and you see these ceramic caps, again, very, very dependable capacitors. You left alone most of the time, just like micro capacitors. So that's one nice thing about it is that you let this happen to be capped at that point, which they want to change things all out. So one nice thing about ceramic capacitors is that's what they have with the paper and foils. But again, some of the cheaper, older style amplifiers with engineers and they didn't know what they were doing. These signal changers. Just looking at it, I did a video on how microphonic these things work. Actually, tap them. You can see it on the scope. There's some pretty large swings. So what I'll do is I will link that video below. So just below the video is a description, and below that description you'll see show more written in capitals. If you click on that show more, it'll expose some links underneath there. When you click on that video, there's also some marks that you can see how microphone these caps are. I've had lots of people that are skeptical about that. They're absolutely fine in audio chain. So those are just some of the issues on the bottom side. Again, tune placement and everything. For my own use, I don't want just cable going to a single probe. What I really want on the bottom side is a BNC style connector, so I can put whatever probe on the front I want. And if I also want to, say, test a noisy resistor of some sort, I don't need to fiddle around with the probe with a little bit of a tip on the front and an alligator clip or something like that. I can clip the resistor in, put it off to the side, so I don't have to hold anything, because this thing routes high voltage out of this probe right here, so we can test for noisy components. I'll show you that here in a little bit as well. well. So I want a BNC connector on the front here, something that I can either put a probe on, or an RF probe on, I can just put a pair of alligator probes on a piece of shielded cable, something like that. So this is really what I want. So I can install a BNC here, which is a much better option. Something that I definitely need to do as part of the BNC. Line cord to get fixed up here. This is just a line cord coming right in, there's nothing happening there, so that needs to be fixed. It's coming right off. Why, I don't know. We'll find that out here in just a little bit. So that is just some of the problems on the bottom side here, and you know, after testing this, we may find more. Some people just go through this and take our time, find out exactly what the issues are, and try and solve what we can in this design. So the design is most likely going to be salvageable, but it's, you know, it's going to have some problems that are just going to hang around, I'm sure. So let's get into that. I'm going to also actually, just before that too, is remove this. I'm going to get some black paint on this little grill over here. So I've already got the cabinet off, and I'm going to paint that cabinet. This thing, not doing beige or something. I think that's black or silver or something like that. So screws and tape this off. It's just pinched between the speaker and face it as well. I got the grill out here, so it looks like somebody had drilled the grill wrong at one point. So there's 3 holes here, and also here to the long way. So it's going to get like this. So to get the grill, it was really quite easy. All I had to do was just remove the 4 screws on the face and just slide the grill out. And the speaker itself is in a very nice condition. So what I'll do now is I'll put the screws back in, just hold the speaker in place, and I'm very careful, and I'm going to poke at it, and repaint this grill, and that's what I'm still kind of excited to go and slide the face.
I'm ready to start blasting case right now. So right now it's inside of a big blasting ground. The reason here in the background is a vacuum with a big filter in it. What it does is it draws air through this case, and then of course filters that air out. When you're blasting in a case, it's very dusty in here, so it draws all of that into a canister with a big filter in it, filters it out. So it draws air on the back side of the cabinet. So what I'll do is I'll put my mask on here first. I'll get a little bit muffly sounding, and then what I'm going to do is grab the glass blaster and start taking some paint off. I'll show you how that works. There we go. Get the mask on. Right down here. So you can see how quickly it takes that down to bare steel, raw steel right there. So the process is really, really fast. It'll clean this right down, and it's pretty much ready to paint directly after that with that hammer tone style paint. It leaves a nice surface on top of the unit itself, so the paint really sticks well. Before I paint it though, I'll use some brake cleaner, things like that, to clean the steel off to make sure that there's no wax or oils on it. Don't want any problems with paint sticking to the metal, and it is in this large cabinet here. So that's the glass blaster, so I'll keep on going and get the entire unit all blasted, painted. Should make a really nice looking cabinet. I'm looking forward to seeing what this looks like when it's all painted up.
To start the troubleshooting procedure on this signal tracer, the first thing that I'm going to do is get some basic stuff out of it first. So I'll solder out these terminals here. I'm going to put something underneath here to press this wire link. It's actually touching these terminals. Solder and melting these wires here. So I'll get these 2 terminals soldered up. That was obviously forgotten during the assembly procedure. And then what I'm going to do is cut out the remainder of this line cord and get rid of this sort of string cord restraint on the backside here. Get rid of that during the testing procedure. I'm just going to put a cord in here temporarily while we're doing this. Reason being is the hole in the back panel that fits on this unit is not large enough to fit a plug through. So I actually have to put the panel onto the back side here and then put the cord through both. So I'll show you the hole in the back panel here in just a little bit. The plug is pretty wide, the hole is pretty small. So just for testing, I'll get rid of all of this stuff here and feed a line cord in, and we'll begin the procedure at that point. I had to remove the water heater socket from the front of the unit so I could clean these incredibly oxidized glass. They would not take solder at all. So I could apply a flux feed solder and just bottle up and roll off. So after a little bit of time working with this in the chassis, trying to make it accept solder, it just that's it. So I ended up cleaning this thing up really well, applying our flux again, and then working solder on the surface so it's pretty thin. So this thing back in easily accept solder. These were very, very stubborn. So that's fixed up. I'll reinstall this. Some more screws in the front while I'm at it. I temporarily installed a line cord with a single tracer. This line cord runs off an intermittent isolation transformer in variac supply. That supply is going to allow me to safely bring up the line voltage slowly. Now, if there are any issues in this unit, major issues, that current limited supply is going to take care of that, and I'm not going to cause any further damage to this little signal tracer. If you recall, they did cut the line cord off of that, so there might be something majorly wrong with that part. Again, we'll discover all of these issues together. What I want to do is I want to bring you through the entire troubleshooting and repair process. So when we discover a problem, we're going to take a look at that problem and see how that problem affects the rest of the circuitry. That is absolutely crucial in troubleshooting, not only just repairing the unit, but actually understanding why the unit is acting the way it is in its failure. Again, very, very crucial in troubleshooting. So we're going to do that together. Now, if you're following along, you're doing so at your own risk.
know that there is high voltage present all over vacuum tube gear. In this unit, there's AC line open, AC just right here, this, here. In these older pieces of gear, they didn't take the time to put HINO tubing over everything and make sure everything is basically safe. They just expected you to know that this is dangerous, and this is very dangerous. So all vacuum tube equipment has high voltage present all over the place, and aside from space charge circuits, I'm talking about but most vacuum tube gear has high voltage, and some of it's extremely high voltage present. And of course, we have the AC line present, which is high voltage and high current there as well. So if you're unfamiliar with working on a unit like this, let me do the dangerous stuff. Stay away from a unit like this until you're familiar with the circuits, until you're comfortable with that circuit. If you are not comfortable with working on circuits like this, don't work on them. Don't put yourself at risk. There are lethal voltages and lethal currents available in this chassis. So again, if you're following along, you're doing so at your own risk. Be very, very careful. I'm ready to apply AC to this. Let's see what happens. So, let's apply. All the current is applied on very, very dim. So there wasn't really excessive current earlier. So it's just making a really bad racket. So let's look into why it's making a racket. So far, we know that this very small signal transfer has a very big hub, and we figure out where that hub's originated. Now, in an audio amplifier circuit, hub can be caused from a whole bunch of different things, and that's really what this thing is. It's just a very sensitive amplifier with a high gain stage in the front end. So the hub can be originating from a signal path. It can be either to cathode leakage in one of the tubes or both of the tubes, or it can be main power supply hub. So main bus supply might have ripple on it. Now, the very first thing to go and check is the power supply. And what really points me towards the power supply in this little unit is that the hub is so incredibly strong. It's incredibly loud on this end. So that tells me right there that I should be checking the power supply first. Now, here's something to always keep in mind whenever you're working on an audio amplifier. In this case, this is the B+ supply, and we're supposed to have nice, clean, filtered DC at this point. That's what this capacitor is here for. It's to take the ripple off of the DC so that you have nice, clean DC. Here's the thing with high gain audio stages, and this applies to phone stages and even audio gain stages. If there's any ripple or AC present on the power supply, since the power supply is powering up the amplifier stage, what it's going to do is it's going to take that ripple that's present and insert it into the amplifier stage. And what it's going to do is get amplified all the way down the line as you get closer to the output. So basically, it's taking the noise from the power supply and amplifying it and making it worse as it gets further down. So the more gain stages you have, the more it's going to take that ripple that's kind of leaking into or mixing into the amplification channels and take it really, really bad. So it's very important in very high gain stages and just amplifiers in general to have a very, very clean DC supply. Now that's another thing that brings me to the design of this thing. I look at this and I see, okay, two red leads coming out of a transformer. So immediately when you see a transformer with green and red leads, so green, red, and black, you know, green is the filament leads, red is the B+, and black is the AC line. Sometimes it's black and red. But anyway, I just did a video on Patreon explaining how to recognize leads on transformers. So if you're interested in that, you can Patreon check out its entire video based upon that. And also determining transformer impedance as well. There's some equations out there, math equations to help you figure out how to determine the impedance of audio transformers on your own. But anyway, back to this. So we know that we can see these two red leads, these are B+. One of the red leads just tied directly to the chassis, and we see the other red lead going right into this diode. So one diode. That means that we have half-wave rectification. So half-wave rectification going through a resistor and then directly into a filter can. And if I look at the filter can, there's hardly any. It's hardly filtering it from the or something like that. I'm just looking at this, just going, what is going on with this design? Anyway, it keeps getting more interesting as we go. But then let's fix one problem at a time. So let's see how much ripple is going to be present at this point, if there even is any. You know, so let's take a look at this point, and if there is ripple there, right there, you know that this capacitor is most likely going to be a fault testing cap. So let's do that right there. So I'll take the black lead of my meter, and take the red lead and put it right here onto X. So this is right where it comes out of the diode, this right to the very first filter capacitor. Turn this on to AC, and we'll turn on the backlight. So now what I'm going to do is turn on my variac and isolation transformer, which is going to give this AC line voltage. I'm not going to leave this on for too long because I imagine the hum is so incredibly intense on this, and it's probably really hard on that small audio transformer. So what I'll do is I'll turn on the supply now. I'll put the speaker off in a second when it starts to hum. I'm fingering the switch here. Look at the amount of AC there. That's supposed to be clean DC. It's almost 9 volts. There is 9 volts. 9 volts AC. And take a look at the ripple here. 9 volts AC at that point. So I'm going to shut this off. So there's only supposed to be DC present right here. And there's AC on there. So to give you an example here, what I'll do is just over here to DC. So you can tell that we do have some form of filtering here because there's DC that's lower than this point. So
filter capacitor happening over here. And see how it's climbing. So there is something working here. So we do have some form of capacitance in this capacitor. So it'd be very interesting to try this. Why do we have so much? This is not really running. This is one of the dangers with capacitors. So this is called dielectric absorption. Capacitor, there's nothing applied to this where the power supply is off, there's really applied to this. As you can see, that's just firing up. So this is the kind of stuff that gives tension to shocks, and this is why it's so very important to safely discharge your capacitors, because that means and some of our very large capacitors, that'll climb up to 100 volts. Sometimes even 200 volts will go right back up there and go after sitting for a long period of time, so it's really, really dangerous. Let's see, this is so what I'm going to do now is I'm going to turn the AC supply back on. Now this is the same point where there was AC. As you can see, there's DC there as well. And we have about 130 volts of DC there. And I'm click on the speaker again. So we have a lot of ripple present at this point right here. We need to figure out why there is a ripple there. So what we're going to do is check these capacitors. What we'll do is we'll solve the leads off of these capacitors here. We'll verify this and see how close they are to the actual spec. I've desoldered all the leads from the three capacitors in this one can, so we can test each section individually. So all three of these capacitors have one common ground, which is attached to the can, and the can is soldered to the chassis. So we can just take the negative reading of the capacitor tester and attach it to the chassis, just test each capacitor. So I'll turn on the capacitor tester right now. Now there should be two 50 microfarad sections and one 20 microfarad section. So let's see what we get here. One section has half, or just under half of a microfarad. Same thing over here. This section here, this one here. And same thing over here. They all look pretty close. So that makes me wonder if the actual grounding has just come off from the cans. I usually what they do is they take the common ground from all three capacitors, twist them together, and then attach one wire to the can. So let's just test between the capacitors themselves. And yeah, that's what capacitance there. It looks like the negative has come off here. So it attaches to the actual units with the coil box. In terms of the shorting on top of the sides, it definitely damaged the capacitor. So that's the reason we have so much hum here. So what I need to do is replace all three of these capacitors. Now the capacitor itself isn't leaking. It's absolutely fine. Just leave this here. What I'll end up doing is I'll put in a terminal tie strip somewhere along with the three modern capacitors in. I put those three modern capacitors in, and the terminal tie strip will make it very easy to service down the road as well. You can just take the out. Suppose it fails, so that's what I'll do right now. I'll put a tie strip in here, all the capacitors in here, and try again. Actually, what we should do first is I'll give you an example of how the transformers are coupling on the upper chassis. This is a bad design. So I'll give you an example. So the B plus is completely disconnected. So this just runs nowhere right now. This 220 ohm resistor is just completely open. So we'll just fold this over here like this. And what I'll do is I'll get this attached to the isolation transformer and current is applied. And I'll turn this thing on. I'll bring this up to the microphone and I'll let you hear how loud the hum is in the speaker. So just the set up. The B plus is unhooked on the bottom side, and the two tubes are removed. So there's nothing in circuit to drive that audio transformer just below the speaker. So I'll turn on the isolation transformer and variac supply. So basically what that's going to do is that's just going to apply AC to this transformer. And just like it's this one tube that's outgoing here. So this is the indicator tube for the wattage section. So what I'll do is I'll turn this on and we'll take a listen to the speaker and see how badly this transformer is coupled with this other transformer. So the speaker is off right now, so bring this up to the microphone like so. Watch this. Just from these two transformers being too close to each other. So really the only way to fix that would be to remove that audio transformer below the speaker and place it on this side of the chassis. And it's going to be pretty tight like this and probably going to be on an angle. If I put it this way, I might still get a bit of noise, but probably better than what it is right now because it's so close. Just see the flavors there, it's almost touching. So yeah, I'm going to set this on. Chances are I'm just going to leave the effect of a hum. Just leave that alone. This is probably work, rework, and just knock on that hum. And of course, capacitors installed in the signal transformer. So this capacitor, and this capacitor right here replace what's inside this can. So the first capacitor that was in line here, B plus, there's very first filter is 50 microfarad and 200 volts that's inside this can. That's being replaced by the 2 microfarad at 450 volts. So this is only for the component. That's absolutely fine. The second capacitor is the same as the first one, 50 microfarad, 200 volts. This has been replaced with a 450 volt part at 47 microfarad. That's absolutely fine in this portion of the circuit. The third capacitor here, which was a cathode bypass capacitor, is a 20 microfarad part at 25 volts that's inside this can. That's been replaced with a 22 microfarad 35 volt part right here. So that's a new capacitor here. There's more capacitance in there, voltages, and what's inside that big can. But this is really close to the tube socket as well. Very high quality cans. Again, when I hear something I don't want to repair again, this thing's going to be a multi-work bench. I'm going to use this thing to troubleshoot other pieces of gears. I'm going to let this thing to stay down. This is very The 16 68 k ohm resistor that was tied to this capacitor here with the orange lead is now jumping over here. So I can install a new 68 k ohm resistor right here, and it joins to this area, and then the orange here is just right over here, and it's the short range of this capacitor. So these capacitors. So you can see I moved the resistor over, tie it to this point right here. So this is a ground. This is a ground here. Next one's this like cap. Just bridge these two grounds here. So it's going here. And it's just counted bypass. It's just this counted resistor right here. And that's really all it takes to really calm this circuit down. So we're going to take a listen to the difference, and then I'm going to show you a really common mistake that a lot of techs make, so that you don't make this next time. So I'll turn this thing on. Let's take a listen. There's a bunch of things I'll tell you about here cause text that so called chase the tail on your circuits. So I have a microphone really close to the chassis, really close so you can really hear this. So we have to lift this thing up. That's the difference. Now the little bit of hum that you hear there is a combination of that transformer coupling and basically open line hum, so you can call that signal path hum. It's listening to me sitting on the bench. Watch what happens when I touch the chassis. And that's because this is all unshielded right now, so it's just picking up all sorts of noise. When this is back in the metal case, none of this will be an issue because we'll take care of all the completely shielded aside from the transformer coupling to the audio transformer. Quite a bit of difference there. Quite a bit quieter as well. So this is a real common mistake. A lot of audio guys will chase this hum around. Where is that hum coming from? Where is it coming from? A lot of the times it's coming from them sitting on the bench, or it's even coming from the line cord itself just being too close to the components inside the amplifier chassis. And I'll talk a little bit more about that here in the future. If I add one capacitor from one side of the line cord to the chassis, it can make this thing completely quiet as well right now. So kind of interesting. I'll touch on that a little bit more in the future when we're looking at audio amplifiers and things like that. So what I'll do is I'll shut this thing off right now. And I'll discharge the capacitors. Discharge these caps. Bring it off. This is a capacitor discharge device that is on the top. I'll use this all the time to safely discharge these caps. I'm clicking my fingers in with one of these things turned up. So this is a common mistake that a lot of techs will go. A lot of techs will go into a circuit like this and take a brand new capacitor and they'll parallel with the old just to see if that's where the hum is coming from. Well, you can't do that in a lot of cases, and it'll cause you to so-called chase your tail in a circuit like this because you just won't find the hum if you do that. So what I'll do is I'm going to parallel in just two sections. I'm going to I'll just take two of those sections and parallel them in. So the old capacitor into the new one, so you can watch what happens. Attach this here, and this here. So this capacitor here originally attached to this point, so I just attach it back to that point. And this capacitor originally attached to that orange wire. That's this capacitor now, so I'll attach these to the exact same point. Yes, technically I paralleled in the new capacitors to the old ones. Let's see what happens when we turn this on. Just shut that off. That's nasty. That's the reason that you cannot parallel or use the old capacitor as tie points, even if the capacitor seems to be open. The old capacitor has to be completely disconnected from circuit. This capacitor now. Basically right here. Let's get this over circuit. So you can see the effect of paralleling these things up. It can't be done. The reason that this is happening, if you recall, when we looked at this earlier with that capacitor tester, you can see that basically the negative of the common is blown off, corroded off, or whatever, it's just disconnected inside the can. So these capacitors are connected together because all of those common are still connected together inside the can. So we're going to measure capacitance from one section to the next. So basically what I'm doing is I'm taking these capacitors here and I'm putting these two capacitors across this point here to this point here, and that's what's causing the hum. So I'm effectively bridging two capacitors in series inside this can over these two capacitors right here from this point here to this point here, and that's what's causing that hum. And that's why you absolutely do not use the old capacitor as a tie pair. Very, very important for the troubleshooting. Even for troubleshooting, this is going to bridge capacitors in as much as we can find the hum in this case. Well, now that we've gone this far with some signal tracer, we can machine just put it back together and leave the hum in there because the transformer and it's putting the chassis, things like that. So, as I say, we've modified it to this point. I would just keep on going and let's make this thing the best that we can do. So what I'm going to do is remove this capacitor here and take this transformer and move it over to this portion of the chassis so we can get it far away from the power transformer. You know what I'm going to do is I'll grab a small speaker and I'll take this audio transformer and I'll attach just the speaker leads to this external speaker and I'll hold it up to the microphone and move the transformer around the power transformer and see how rapidly they couple. So de-lacing and shielding, it's still going to couple to that transformer. So let's get this thing out of the way, and then there's another silly thing that they've done in the class as well. Tap on one thing probably. I hope the audio transformer and the capacitor removed at this point. I've installed it on the ground here, so pretty ready to install the transformer and export your chassis. Here's a quick look at the capacitor. Interesting. So since I have the transformer removed, what I'm going to do is move it close to this transformer and put this speaker up to the microphone here, and you can hear how badly this will couple with that transformer. Let's up the speaker like so. So you can see how important component placement on the upper portion of the chassis is, and that's so basic. You want to do wider mounting most transformers like this. So, I say probably an experienced engineer or something put this thing together. So all we do is mount that transformer over here like this, see how much that knocks the hum down, and then we'll go on to the next thing that will be affected. The transformer is now installed, and it went pretty quick. So let's take a look at the bottom portion of the chassis here. So I installed the terminal tie strip here, and just ran the wires off area, area. On this portion of the chassis, what I did is I just soldered the column. Focus here, column, on the transformer to the chassis, because the speaker itself just rounds to the chassis, and then the green wire was the perfect length for it. That's right back up to that switch again. So that worked out very, very well. So I'll get this all positioned, plugged back in, and we'll see the difference in the hump. Okay, let's take a listen and see what difference that made in the transformer. Whoops, I'll get a switch transformer in the ground supply right now. Just the transformer bearing supply. That made a huge difference. Touching the chassis because it's picking me up. That made a big, big difference. And there's still something else we can do with that as well. So that was definitely a worthwhile modification. So the next thing we're going to do is look into a hum balance control. Taking a look at the Stark model ST-2 signal tracer schematic, they've done another very interesting thing in the phone circuit that we are going to correct. So normally in a balanced phone system, the center tab of the phone line, which this does not have, would run to chassis ground. Or in a case like this, where we don't have a center tab on the line, we run a separate hum balance control, which is just a VR across the line, so from end to end on the winding, and then the wiper would run off the ground and adjust the VR for the hum and start to do things. Well, what they've done here is they've used the highest gain stage vacuum tube, and they've taken the filament center tab and they're running that to ground. So that's going to be corrected, and I'm going to put this VR into the chassis. This is a 2.5K VR, and I'm going to adjust this for the hum. So I'm going to put that somewhere on the chassis where I can very easily get to it. So right about here, there's a little open spot over here, so I'm going to remove that panel, and I'm going to get some hum balance adjustment. I'm just going to take that panel off of it right here, screwdriver in, and adjust it. There is an open area under here. So I'll get that hum balance control installed, and I'll show you how that works, and we'll try and reduce the hum a little bit more. Alright, let's adjust the hum balance control. So I'll turn the unit on. Warm up. There is its point at this point. So it's working out very well. So all we do is put the BNC jack in front of this thing, change this capacitor right here, another 0.2 microfarad capacitor here, and I'm ready to try the thing out. The hum balance control VR is installed right here in the chassis. That's at the back side of the chassis. You can see the twisted filament lines are running over here to the filament pins on this tube socket. Now notice that these brown ones are a little bit smaller than the green ones here, and that's absolutely fine because these are really carrying any type of current. The wiper for the hum balance control runs all the way along here. You can see that black one runs all the way over here up to the tube socket here to a low hum point on the chassis. Now when I say low hum point, finding the best spot on the chassis for a star ground is a little bit of a job in itself in the design, just because the chassis itself is carrying current through it. And if you bring the ground on certain points of the signal path to different parts of the chassis, you'll notice a hum. And then just say you had a wiper, you're dragging, say, an alligator foot or something along the chassis, you would hear the hum get lower and lower and lower as you get over here, and as you pass the spot, the hum would start to pick up again, and it's louder and louder and louder. It's going to be louder by the transformer. And as you get over here, it would get pretty loud. So then as you drag the alligator foot back over here again along the chassis, you would find that the lowest hum point is at this point here. And that's a real trick in amplifier design. Whenever you're designing an amplifier, you want to find on the chassis where the best ground is. And that's why a lot of amplifiers have a star grounding system. That's quite a bit different than in an RF application, because in an RF application, having long lead length means inductance, and you cause lots of issues with long lead length. In audio application, it's absolutely fine to have that longer lead length because of the lower frequencies that the amplifier is dealing with. It's not dealing with higher frequencies. I'll talk a little bit more about this in the future in different types of designs, and this applies to everything. This applies to modern equipment, this applies to circuit boards, this applies to everything. Longer lead length means inductance, and when you're dealing with RF circuitry, that's your end. Again, since this is audio circuitry and the frequencies are much lower, you can get away with that, and there is a balance point too. So by having that longer inductance, those longer lead lengths in your audio circuit can actually be beneficial. Again, I'll talk more about that in another video. That's an entire topic within itself, right? So finding the correct ground zone. So anyways, this is a part of the chassis where the hum is very low, and this is far away from the transformer, and this is where that 12AX7, that 7225 is mounted right over here in this area. That's the reason that I did just ground this over here. I ran the ground all the way over here, this area. So that's all done. I've installed the BNC connector on the front here. So I'll show the front. I've also put the speaker grill back in. It looks really nice. So there's the speaker grill. And that's got the hammer tone finish on it. It's kind of hard to tell the hammer tone because it's got some holes in it. But that's a really nice color. Almost like a really dark black, kind of like an ash, smoky gray kind of color. It turned out really, really nice. So BNC's in here. Everything's all ready to go. So I put all the different probes on this. This cleaned up really nice. Now there's still some scratches around the board, but that's where this actually meets the case itself. It has that curled edge on it. So it meets this. So all in all, there's a few scuffs on the face, but it's looking really, really nice. It cleaned up very well. It's cleaned up everything. So since I'm using stainless hardware, I also changed the screws on the face with some nice screws. The other screws were rusty and it looks like something had stripped them. Tightening because they were too tight. Hard the screws, so I put all stainless screws in the face here. They're all matching screws, so that worked out very nice as well. So this is cleaning up really, really nice. I really like the look of that part. Much nicer than that horrible beige color. And the case is the same color as this. You'll see that here. You just hold it. The case turned out just really, really nice. I'm very happy with the case. So all in all, it's coming together. The next thing we really have to test on this is the watt meter section, and that has to do with the eye tubes. We want to make sure that this little area is working well. What this thing does is you plug an appliance or whatever in here, and you rotate this knob just until the shadow angle starts to open. So there's a little gap in the shadow angle, and then wherever it's pointing is how many watts it's drawing. So it's almost like a CRT. These are almost eye tubes. So, but anyway, we'll see how well that works. Plug different loads in here and turn this up, and we'll see how accurate the little watt meter is on the face. It's handy to find out if you're going to test an audio radio or something like that. You can't really bring it up slow on this. This is just not running all our watt meters. If you plug anything into this, and it is pulling excessive wattage, you know, there's not really anything to confuse it or something like that that's going to deal with that, right? So this is where a dingwall tester really helps. So something like this and a dingwall tester combined would be a really, really good design. And I tweak for a watt meter, and dingwall tester bulbs light up really good. You can tell if there is something wrong. Again, this thing, if you plug it in, you know, it's just going to show extremely high wattage if something is really wrong. By that time, usually, by the time you've sensed all that kind of stuff, it's almost too late. But still handy. You know, there are applications where the watt meter goes really nice. So make sure that this portion of the circuit is working. Now everything is working. The hum is about as low as it's going to get at this point with all of these modifications, unless of course you want to change this one capacitor and really up that capacitance. You'll recall when I looked at the design, so, you know, this is it's kind of low. There is no filter on this side here, so it's going to drop the ripple down quite a bit by installing the new capacitor. So you heard the difference in the hum. It's pretty crazy. I'll talk a little bit more about that, and what I'm going to do is I'm going to show you some examples of the results now that these capacitors are changed and what you can expect. And I'll talk a little bit about what you can expect when servicing a half-wave rectification design, whether it be an All-American 5 or All-American 6 radio, one of these devices or something like this. So this is something to keep in mind, and this is something that really isn't talked about a whole lot. So you'll get some first-hand examples of exactly what to look for if you're dealing with a design like this, or as I say, a radio or something like that. When the troubleshooting procedure began, this little signal tracer had a lot of hum. That led me to check the very first capacitor, and the plus line is attached to this end of this resistor over here. So this resistor here, and attached to one of the legs of this can, as well as those little wires as well. Since I've installed more capacitors, I've put a capacitor over here, and I've installed more capacitors like that, excluding the cathode and bypass capacitor, which is attached directly to the cathode to the side. So all I've done now is I've taken this resistor and bent it over here to the new capacitor and attached everything over here on the terminal capacitor. So everything is as it was over here. It's just mounted in different areas of the capacitors. Now, if you recall, when we measured the ripple at this point, it was incredibly high, 9 volts AC or something over here. So let's compare the new capacitors to the faulty capacitor and see how much ripple is at this point now with these new capacitors. And this capacitor here even has some more capacitance. The original was rated at 50 microfarad. This is now 80. So let's take a look. This thing's on and it's warmed up. What a difference. 9 volts down to 1.3. Now some of you are saying that's still a lot. 1.2, 1.3 volts AC there. And that nice sawtooth looking waveform on the scope there. Want to know what's even more interesting? Is this point here is what basically powers this tube down here. So this is attached to this tube through the audio transformer. Why is the hum so low? That's what I want to think about that. Let's test the ripple at the second capacitor. And that's incredibly low. Why is the ripple lower at this capacitor than it is at this capacitor? Okay, what's between these two capacitors? This capacitor here is the filter for the preamplifier tube, so we will definitely have low ripple at that point. So since this is attached to the preamplifier tube and we need low ripple for the preamplifier tube, why is it okay to have 1.3 volts of ripple on the output tube? Yeah, that's what I'm think about that, try to answer that. So now, we have lots and lots of ripple on this very first capacitor. I'll try and throw you a couple of curveballs here to see if you can get the answer to it. So what I'm going to do now is I'm going to shut this unit off. And And I'm going to take a 47 microfarad capacitor, the same capacitor that's over here, and I'm going to put it in parallel with this one. So I'm just going to go right across this one. What do you think is going to happen if I do that? What do you think is going to happen to that ripple? Make your guesses now. So what I'm going to do first is make sure that these capacitors are discharged. They are discharged. Another question you may be asking yourself is, why are you continually going in there and discharging these capacitors, making sure that they're discharged? You can't see any glow on these LEDs. They always seem to be discharged when you go in there. Well, the answer in short is the tubes themselves are discharging these capacitors because of the thermal mass of the cathodes. These are indirectly heated vacuum tubes. They're not directly heated, so there's no thermal mass in them. But you can never be too safe. You always want to make absolutely sure if there's ever a fault in the circuit, these capacitors could remain charged. So if you want me to get a little bit more into why these are discharging and what's happening with the thermal mass, then I'll quickly touch on that. So the heaters inside these vacuum tubes are inside of the cathode sleeve. So there's a filament like what we see in the light bulb, but it's tucked inside a little pipe inside the vacuum tube, and that filament, when you turn the unit on, it applies heater voltage to that filament. The filaments inside start to glow really hot, and those filaments have to heat up that pipe. That pipe is the cathode, and it has a special coating on that cathode, and the cathode is what emits electrons inside the vacuum tube. So in order for the vacuum tube to work, that pipe has to glow orange so that electrons have emission inside the vacuum tube. That's what both of these tubes is. Now some tubes are directly heated and some tubes are indirectly heated. These tubes are indirectly heated, so it takes between 10 and 20 seconds for the filaments inside that pipe to heat that pipe up nice and orange. That's why when you turn on the radio, it takes a while for the radio to come on. If you have a vacuum tube amplifier, turn on the vacuum tube amplifier, it takes a while for the signal to come out. It's because those pipes have to heat up, so there's a thermal mass inside. Well, the same thing happens when you cut the power to the power supply. So if I shut the AC line off, so shut it off either here or by the switch, of course the whole power supply and everything's going to shut down, and the heaters inside the tube are going to shut off, so those filaments inside that cathode are going to get cold. Well, since there's so much thermal mass inside that tube, that cathode is still glowing orange, but it's slowly cooling off. Well, as it's slowly cooling off, because the power has been cut, the tube is still working. There's still electron emission happening. So what's going to happen? Since it has no power supply powering up these capacitors, what's going to happen to the caps? Well, these things are going to do the work now. What's going to happen is the tubes are going to use up the charge inside these capacitors. It's going to drain those caps off really, really fast. So these things are kind of acting like batteries for a very short period of time when you cut the power. So what's happening really is the tubes are staying into emission longer than these things can supply the charge, so it drains these things right off. Here's the thing, if you have a very, very large capacitor in the power supply, the actual capacitor may supply enough current to those tubes as the cathode is slowly turning on to still end up with a lot of voltage. So you always have to make sure that the capacitors are discharged or they can be under voltage working in the chassis. And in some cases that could be lethal, just depending upon what type of a situation you're in. Some of these big vacuum tubes have huge capacitors inside, and you shut the amplifier off, it'll drain the capacitors so much, but there's still a little bit left. And then after that, we get into another subject, which is called dielectric absorption. It almost appears like the capacitors are charging themselves back up and down, but they're not. Really what it is again, it's dielectric absorption. We'll get into that in a future video. So it'll drain the caps off, and then there's no more emission in the amplifier. The caps are sitting on it, and it almost appears like you're charging nothing. So I'll touch on that in the future. So what I'll do now is I'll grab that other capacitor. There's so many different things I can explain. I can make so many different videos on all of these topics. So I will make a video on this kind of stuff here in the future. It's just that if you're talking about all of these small units, it's supposed to be this video. So 47 microfarad capacitor in parallel with this one. So this exact capacitor is putting it across this one. So now we have a lot more microfarad. So we have 82 microfarad plus another 37 on top of that. And the leads are fine again. No touch, short out. So now I'm going to turn this thing back on again. What do you think is going to happen to the ripple? Your guess is now? Here we go. On. And I have something that's going to throw you for a loop again. This again, a lot of the older techs probably be shaking your fists. So here we go. Now that I got this cap installed, what do you think is going to happen? What are we going to see on the display? AC volts. Your guess is here we go. So drop it down to about 0.85. But as you can see, it's still pretty high. There's a lot of ripple at that point. It's still limited to 60 hertz right there. So we dropped it down a little bit. So why is it so low at this capacitor, and yet it's so high at this capacitor? Let's take a look at the schematic. So we shut this thing off. One more thing that's going to really force it. Might also be asking what you're doing, why are you doing this? Well, I'm scrubbing the leads. So if there's any flux or any kind of residue on the lead, I want to make sure that I've got a very good contact, so I scrub the leads. And that little kind of little ridge that you see there, that little ridge that you see in your probe right here helps with that as well. So basically what we do is we go over to a lead on something, just scrub it like this just to make sure I've got a very good contact. Just to make sure these caps are very well discharged. I do that a lot when I test for voltage as well, and scrub leads. Sometimes you find flux or something, you get into the probe, and it doesn't make a good contact, so by scrubbing, these caps are discharged. What's Paul going to do next? Let's take a look at. So here, we have another capacitor that we're going to put in line, and we're going to see what happens to the ripple if we install this capacitor right at the diode, okay? And I'm not going to be shy with the ratings either, so here we go, 200 volts, 200 volt rated cap, same thing. Difference is, wow, 820 microfarad, approaching 1,000 microfarad here. I'm going to put this capacitor right at the output of the diode here, so right at the it's basically coming into this resistor, I guess you could say. There was never any capacitor here, and it's not even in the schematic. So I'm going to put 820 microfarad right at the output of the diode. Somebody texts it, you can't do that, that's 820, it's going to cause damage. No, it's not. Here we go, right here. So right at the output of that diode. Why this capacitor will not cause damage to this power supply in any way, shape, or form, and this can actually be left in the chassis and will be fine throughout its entire life. I'll explain all this stuff in some future videos. Again, I could just keep going about some small details, and there's just so many things to cover. So a lot of the techs out there think that you can't go about doing this kind of stuff. All it's going to do is blow up the diode, or part of the transformer, the transformer will deal with this. I've heard it all. All of that is absolutely false in this case right here. It's absolutely fine. And we can deal with it. Okay, so here we go. The capacitor is hooked up to the power supply on. So everything's on, it's warming up. They think, oh, it's got to be awfully hard on that diode or the power transformer, right? So what I'm going to do now, you'll be able to tell by looking at the blowing pipe there, you know what I'm doing. This is what I'm going to do is I'm going to shut the power supply on really fast. So what's going to happen? What's going to happen this time, right? Here we go. Turn it off. We're going to switch clicking. So many times, really fast. It's off right now. On. And I'll do it again. So now. It's on again. Why is that? I'll explain that in a future video. This wouldn't be so incredibly tolerant if this had a vacuum tube rectifier. This is a lot of capacitance, and vacuum tube rectifiers have a bonding wire that run from the cathode, so this is an indirect tube, okay, so say we're talking about so 35W4 or something like that. And say there's a bonding wire from the cathode to one of the readout pins, okay, so what happens is that bonding wire decides that tube acts as a fuse, and so does the filament itself, and that's why you see a lot of polymer fiber needles within the fuse. If anything goes wrong, it just blows that bonding wire off, and of course the next weakest link is the filament itself, so it's really no need for fusing unless you want to be very, very safe in that. I still do. I still like fuses. Technically, that's what I'm doing for fusing. So there's a bonding wire in that tube is the weak point, and this thing right here will cause problems with that type of vacuum tube, especially if this is a diode right here. So it's absolutely no problem. So understanding why nothing happens to this is really just, it's a talk about the amount of current that the transformer itself can supply. I'll get into all this stuff in the future. So here we go. Let's take a look at the ripple now at this point. So this is a really nice feature capacitor right at the output of the rectifier. Okay, so here we go. Look at how low that is. What a difference. From almost a volt down to, say, tons of volts. Let's say 20 volts or something like that. Now let's go look at the second one here. This is the one that's powering the preamp to the filter cycle, I should say. Look at how low it is at the beginning. Just hunting. So there you go, incredibly low with an added filter capacitor like this. Now, why in the day wouldn't they put something like this in the chassis? Well, A, cost. Back in the day when this thing was made, 820 microfarad, 200 volts was a monster-sized can. And way back when, capacitors like this were very, very expensive. So to purchase an 820 microfarad capacitor at 200 volts was very cost-prohibitive in a design like this. So what they did is they got creative, and they did this, and they used the same kind of topology in All-American 5 and All-American 6 radios. This topology here, excluding this large capacitor, so the original topology, they used that in the 5 and 6 radios, and they could get away with it. Why could they get away with it with so much ripple, and especially that ripple being tied directly into the audio output to it? Why could they get away with that? Well, what I'll do is I'll grab a schematic here, and I'll explain a whole lot of things to you why all of this works, and it works not too bad. Of course, leaving this in here right now would knock the hum down. We can even take the hum down a little bit more, but at this point, it's so incredibly low, adding this capacitor into the circuit, it's only going to take it down just a little bit more than what it is, and at this point, it's a balance. Right? At this point, it's a balance. If I wanted a very quiet circuit, this is a signal tracer. This thing isn't an audio amplifier. It's not a radio that's going to sit by the bedside and you're going to be listening to it late at night to your favorite radio show or whatever. It's a signal tracer. It sits on the bench. It usually sits far away from you, and it's used as a test tool. So that little bit of hum that you heard earlier before was just a capacitor. It's completely tolerable, especially now that we've done all of these other modifications. Move the audio transformer and the hum down. It's just so much better. So I'll get the schematic and I'll start explaining all of this stuff. The modifications to the Model ST-2 signal tracer are as follows. The filament center tap of the 12ASI is now open. It no longer ties to chassis barrels confined to the filament. A variable resistor has been installed across the filament winding, and the wiper of that variable resistor now attaches to chassis ground. The rating of that variable resistor is 2.5 k ohms, so that gives us unbalanced control. T2 has now been relocated. Originally T2 was too close to T1 and they were coupling, giving quite a bit of hum at the
speaker. T2 has been relocated to where the original filter capacitor sat. The value of C8 has been changed to 82 microfarad. The value of C9 has been changed to 47 microfarad. The value of C7 has been changed to 32 microfarad. A BNC connector or jack has been added to the face of the unit, so it's been modified so that it can use different probes with BNC connections. The line cord is still temporary. I haven't installed the line cord permanently at this point because I need to put the back on the unit. The hole in the back panel was a little bit too small to fit the plug through. The 68K resistor has been replaced with another 68K resistor just because I had to relocate it, and the original resistor was too short because it was installed into a different area and so I had to replace the entire resistor. Other than that, components have been moved around a little bit, and just moved around, wires have been moved, not much has been changed. Now the wattmeter section still hasn't been checked yet, so this entire circuit, we're going to do that here in just a little bit. We're just getting the amplification chains and basically the signal tracer out of the way first. So if you recall, at this point here we have 1.3 volts worth of ripple. Now this one here, if we follow this path, runs down here into this switch. If we give this switch one click clockwise, pin 4 and 5 are going to connect to pin 7. Pin 7 is acting as a wiper, so when we click this larger area, we'll contact this arrow. These two are ganged, so these two switches will do the same thing. When I say gang, they have one common shaft in the switch. So now this is now connected to this point. So technically this point here is now connected to here. The B plus now goes through a 10K ohm resistor into this 47 microfarad capacitor, up this path to the screen grid of the 12CA5 tube, and up this path here to the plates of the two sections of the 12AX7 here. If we also follow this path down here, we'll also see this point here is connected to this point here at this point, and it goes down here. Since we clicked this one, click clockwise, again, pin 4 and 5 will be connected to pin 7. So now this point is now connected to this point here. So we'll see a direct connection from this point with lots of ripple right directly into the audio transformer and to the plate of the 12CA5 here. Now you're saying to yourself, that's a lot of ripple to be on. How come this thing isn't coming a whole lot? Well, they chose the 12CA5 because of its power delivering capability. This is designed to drive an audio transformer. So there's not a whole lot of amplification happening. There's a little bit of ripple really isn't affecting the circuit. Remember, this transformer here is doing impedance conversion. The 12CA5 tube has a very high impedance, and we need to take that impedance and convert it or transform it to a lower impedance that will better match our speaker. That's what the transformer does, which is basically taking this high impedance and converting it into something that will draw the speaker. So not a whole lot of amplification here. Where it really matters is in the plate supply of these two tubes, but you'll see that the B plus goes through this 10K resistor here and gets filtered again by 47 microfarad capacitor, and of course that feeds the screen grid and the two plates of these tubes over here. You can see the path all the way here to the two plates. Well, why is there less ripple at this point than there is at this point? Well, we have another capacitor here, and we also have a 10K ohm resistor in the path. So the strength of the ripple is greatly reduced at this point. So by putting another capacitor here, we can almost virtually eliminate it. And there's so little ripple at that point that it's not really affecting the amplification chain all that incredibly much. That's basically what's going on. So if we look at this circuit here, when I installed that really large capacitor, that 820 microfarad capacitor, I put that at this point here to ground. So basically right at the cathode of this diode here. So what's really happening? Well, we're adding a whole lot more filtering in at this point here. Now, if we get rid of the ripple, what's going to happen to the DC? The DC is going to push it up. This is going to go up to about 160 hertz or around that area. And we're going to have about 150 volts over here. Well, of course, it's going to up the voltage a whole lot to the circuit. It's really not going to affect these two incredibly much other than take this out of its design parameters a little bit. But again, way back in the day, they didn't have capacitors like that available, so they had to do with this particular circuit arrangement. And as you can see, it works very well. Still just a little bit of humming there, but it's livable. It's not really worth adding that extra capacitor in there at this point. And that's really what's going on in the circuit. Now, if we take a look at parallel, the old capacitor, so the old one that was faulty, if we were going to parallel that into the circuit, why would putting these new capacitors in the circuit not affect this? Why would the hum still be there if that old capacitor was there? Well, this is the reason. If I take a pen, stuff on the desk. We have 3 capacitors in that old can, technically. Okay, so I'll just draw 3 capacitors quickly here. So this goes off to the can or to ground. We have our 3 capacitors here. So now, since this is the can and this is tied to ground, we know that this is open. So this is blown open and rotted open inside here. So now we have 3 capacitors just attached together, and this is completely missing. So if this was the 50, this is the 50, and this here was the 20 microfarad capacitor. So since we have 2 50s, we have one here and one here. What's happening? Well, we have a path like this going through here, and also going through here. We'll just ignore this for now and keep it simple. So we have basically 2 capacitors in series. So if we're to look at this, we can get a capacitor here, and a capacitor here, and we could just take that and tie that to this point right here. Not joining these 2 lines here, but just attached to this lady right here, okay? So we're now taking the ripple from this point and putting it through these 2 capacitors right here, completely bypassing this component right here. And we're taking that, all of that ripple
ripple that was originally there and put it here, and that's the reason we made this entire circuit here, because we have a path right through here like this, and that's why we can't parallel these reasons. So if something like this happens, you're kind of almost fooling yourself into continually searching for that hump, because you put those new caps in there and the problem wouldn't get solved. So that's really what's happening. So if we wanted to really shorten this up, we could just put it like this. That's really what's happening at this point. We've been bridging this out, we're taking the ripple from this point and putting it right here. So that's the reason the hump didn't disappear when we parallel using passwords originally. Okay, let's check to see if the watt meter works. Light socket and a 40-watt light bulb. So screw this in here. And now just before I completely connect this here, what we want to do is move this just until the shadow angle just starts to open. When that shadow angle just starts to open, this should point to the appropriate wattage. So give me an example. Turn this on. There it is. Get that out of the way. So now what I want to do is I just want to rotate this until this opens. And you can see it's starting to open about 30 to 35 watts. So it's a ways off. Let's remove this one here. Now, the 200 watt light bulb will spare you from that. Okay, so here we go. And it's not too incredibly far off. This seems a little bit high. It's not too bad. Not too bad at all. This is a little out, isn't it? Let's make sure that everything is okay in that circuit. Let's take a look at the way the watt meter portion of this circuit works in this small signal tracer. Really, it's quite simple with the circuit, but it uses a very specific component. It's quite simple as well. So I'll explain how it works on the schematic, and we'll take a look at some components in it, just make sure it is working in case it really goes off a little bit. So first of all, we close switch 4 on the face of the unit, which is the main power switch, and it closes the switch here, and it takes this portion of the line port and puts it at this point of the winding of T3. T3 is this little transformer here. So this end of the winding is placed in series with the load. So whatever you plug into the face of the unit, that's this outlet right here. Whatever we plug into that outlet is placed in series with this winding. So what does that tell us about T3? Well, T3 has a pretty large primary winding. It's a pretty special transformer, and there won't be many choices in that transformer as well. So what's going on? The more load that we place on this outlet, or at this outlet here, the more load it puts across this transformer. The more we load the transformer, the more voltage is going to be present on the secondary. Now, you'll see that we have a 50k ohm potentiometer approximately with the wiper that goes to the diode. So that 50k ohm potentiometer is on the face of the unit here, and they've written in calibrated steps in wattage all the way up to 500 watts. I'm actually going to see if we right to the end of it, right? So chances are this transformer will deal with more than 500 watts. So what happens is, the more load that we place here, the more voltage we're going to get on this portion of the transformer. What's happening here is, you can see we have a diode with the cathode in that runs directly to the chassis. So that means that we have a negative supply right here. So it's creating a negative supply because we're feeding positive right to the chassis, and we're running the negative off this one. We have a 0.2 microfarad capacitor, which is just acting as a little bit of filtering. And you can see we have a negative line that runs off here. It goes through the switch, and it's going to end up at the grid of this 1629 I2. What's going to happen is, the more load that we draw at that outlet, the higher the voltage is going to be, so it's going to be more negative. So when I say the higher the voltage, so if we start at 0, it'll be like negative 1, negative 2, negative 3. The more load we pull, it's going to go to negative 4, negative 5 in that direction. The higher the negative voltage on this line here, the more the shadow angle in this tube is going to deflect. So what that means is, the more load we pull here, the more that shadow angle is going to close. Then what we do is we calibrate this until we can open that shadow angle again, and when we get a little bit of a gap, we look where that needle is pointing in the face, where the pointer on the knob is pointing, and it should point roughly to how much wattage we're drawing at this output. And that's just how simple this circuit is. Nothing more than that. So what we want to do is we want to check the validity of a few components. Of course, the major suspect is going to be as well. So let's check that out first. So what I'll do is, I'll move the I2 out of the way. It's just clipped in here like this. There is no power or anything connected to the unit at this time. I'll just take this out here, lean this down here, and we can get right to the VR. As we can see, that little diode is right on the VR. So what I'll do is I'll get some test equipment placed on the bench here. We'll check some components. The first component that we want to check is the diode. We'll check these components in circuit using a curve tracer. One end of the diode is attached directly to the chassis, and the other end of the diode is attached to the wiper. So we'll just focus on there so you can see that on the clear. So you can see one end of the diode is attached right here, and the other end to the wiper. So what I want to do is make sure that the VR is roughly centered before I do the test. So I'll take the common read of the curve tracer, I'll put it to the chassis, I'll take the signal read, and put the signal read right to the wiper. So the wiper is common read here, and then what I'll do is I'll just move the focus over the curve tracer, and take a look and see if this looks like a diode. And that does not look like a diode. That looks like a resistor. It's really a valve resistor. Chances are really the problem. So earlier on, just going to focus back here. Earlier on, I was placed the capacitor capacitor that was right here. It was a ceramic tubular style capacitor. It was like a big foil inside, with pots on each end. So I replaced that just to be safe. So I'll test this capacitor just to make sure that it's okay. So if the capacitor is okay, I should get what looks like a circuit on the curve tracer screen. So I'm just going to focus back over the curve tracer. And here we go. And that capacitor is fine. So now, if I want to check to make sure that this VR is working okay, so it's working through its travel. Now we looked at the icon, we saw that the icon open and closed pretty easy. Nice and smooth, I guess you should say. So most like, I'll show you what it looks like on the curve tracer. So we'll go on and do something. So I'm going to do this back on the curve tracer. So we'll go from this end here to the center of the VR and rotate this. So as I rotate this, you see how the trace is twisting and right up the top, and that's a short circuit. Now you'll notice how it kind of popped in place. So I'll just rotate this VR in front of the user very slowly. You see that nothing seems to happen. It remains like a dead short for a short period. Now all of a sudden, boom, it just pops into existence at a very small spot. It's very common for a lot of VRs. So if you ever see that when you're using a curve tracer, don't worry about that. As you can see, it moves smoothly throughout its travel. There is no problems with this VR. And of course, we verified that by looking at the actual eye tube on the faces. I rotate the VR. You can see that the eye tube is slowly closing and opening. So no problems there. So far, it looks like this dial is toast. So what I'm going to do is desolder one end of this dial. In fact, I'm going to lift that. This thing here. So let's take a look at the dial again. So the wiper end is open. So I'll just this diode has changed its form to a resistance. It's changed its state. It no longer wants to be a diode anymore. It wants to be a resistor. This diode is resistance. So I'm going to remove this diode here. I'll show you what the proper diode is. So we'll just get that out of the way. Let's take a look at the original diode that I would put here on the curve tracer. So what you see here is I've got the curve tracer attached to my digital voltmeter. So when I designed the circuit board inside the curve tracer, I also doing the sleep circuit, as you can see. When I designed the circuit board inside the curve tracer, I wanted to give it the option of having an external digital diode to take a look at the forward diodes and reverse diodes, etc. Check out transistors, things like that. So that's all built into this. You basically just attach this to any old digital voltmeter anything it has, it gives this oscilloscope, which is now converting into a curve tracer of a digital display. It's kind of weird. So at any rate, we can look at the forward of the diodes here. So I'll attach this in here and we'll work out. So as you can see, the original diode is like the diode indicating resistance. If there's a dead short, you can straight up and down, so it's slightly resistive. So the 134A is a germanium diode, and I've got lots of glass diodes, tons and tons of glass diodes. Of all sorts of different makes and sizes and shapes. This one is really high quality, it's got gold leads on it. And it's another one that I picked out of my junk bin. So if I test this one with the gold leads first, put this on the scope here. So on the curve tracer, we can see that this is the forward here. So if I turn the voltage down, keep an eye on this here, we should take the corner at around 0.6 volts. So let's see about 0.5 volts. We'll start to take the corner right there. So it's just starting to take that corner. So that's the forward of this diode right now, 0.6. So I know that this is just a standard silicon diode. So germanium diodes have a really low forward of around about 0.2 or 0.3 of a volt. So I had to go through my junk bin and find another glass diode that leads all of this. That's okay. So you put this in thinking which way you want. And as you can see, I'm at 0.6 of a volt, but I'm well in the turn. So if I back this off and bring it right down to where it just about starts making the turn, you can see it's making the turn to 0.24 of a volt. So you can see that this is definitely a germanium diode right down there, right? Making the turn there. And it's well in the turn about 0.40. So you can see definitely germanium. So this is what I want to replace this obviously shorter device with. Now, the specs of this diode aren't really too incredibly important as long as it is a germanium diode. The reason being is the voltage on this side is so incredibly low. Right? Only need -5, -6 volts, something like that. So you can see here, watt meter, -5.6 volts at 0 degree shadow. So we're doing really low voltage on this side. So pretty much any germanium diode is going to be just fine to replace this 134A. And that's what we have right here. So you can see it's coming to a turn. So definitely germanium. This is going to go into this circuit, get that installed, and we'll check watt meter again. New diode installed. Let's take a look at what 40 watt light bulb does. Here we go. Okay. Just on opens. Look at that. That's what I want to see. Oh. Okay. Let's try the 200 bulbs. The incredibly hot light bulb. it's sure going to look a lot nicer than that beige color that it was issued. So I'm looking forward to doing the same one here, see how it looks all assembled. So the next step for me is to get the line cord into the unit with the back of the case on. And actually, it's ready to assemble this thing. I'm not going to put the handle back on because I'll probably just put some screws in here to fill those holes. So that looks like something's happening here. And that allows me to put my piece of equipment on top of this as well. This is my full-time workbench. So I'll get this all assembled and we'll try it out. This signal tracer is reassembled. Okay, let's grab something great in that case. The color of the case and the grill really sets off the face and the color combined with the posts just looks so good. I don't know why they didn't issue these things in a darker color like this instead of a beige color. At any rate, it works incredibly well. I'll give you an example. So the game's right off. So it's right at the stop. I'll just put a standard cable on here. That's what the game all on. I'll give it just a little bit of gain. That's just the gain. That's picking me up. So if I touch the case, it gets quiet. This is shielded right up to this point, and it's still hearing me. So you know what's going to happen if I touch this, right? It's just incredibly loud. Whoa. I couldn't even imagine if I had this pointing at 12 o'clock, it would probably destroy the speaker. Incredibly sensitive unit. So this would be great for signal tracing. I'll put on an RF probe that I have. Here's a very sensitive RF probe I designed sometimes back, highly sensitive. So this is for sniffing noise, crackling components and things in circuit. So let's turn this up. So it's just picking up switch mode noise right now. So I'll bring this close to the microphone. That noise is the camera. So that's a switch mode or a bunch of stuff going on inside the camera and the switch mode supply that's powering it. Bring close to another one. It's another ramp. Incredibly sensitive. What else do I have here that makes noise? Anyways, RF probe, very sensitive. Let's see if I'm holding the ground of the RF probe just to keep it quiet. If I shield it with my hand, it's just picking up random switch mode noise. It's louder when the open towards the microphone and the camera. So very, very sensitive. Gain is hardly moving. There's no move there like that. So the noise works well. There's a little bit of a thing you need to know about the noise circuit. Whenever you put these things onto noise, it puts about 100 some odd volts on the probe. So if you don't know that, don't use the noise section in one of these noise tracers. And definitely your signal tracers, you got to be very, very careful with that because you can get a pretty decent zap. There's a high value resistor in line with this so that you can listen to noisy components. I just happen to have one saved in the browser between grab it. We'll do a comparison for you. Two resistors here, high quality Allen Bradley style, and 2% tolerance. And then there's no rounding here. Yeah, take a listen to both of these things. So it's not on noise. You can see that I have it on trace only. You need to remember this with these signal tracers, or you'll buzz yourself. So this is just a newer style Allen Bradley resistor, very good resistor. So I'll turn the gain right down. That's a mean. So I'm going to hold the negative here just so it keeps me quiet. I'm not touching that portion of the probe because that's live right now. And you can hear that's pretty quiet. Very quiet. Look how much gain I'm giving this thing. So I'll turn this back down. Turn it back to trace because I don't want to touch this. So I'll put this resistor in. This one's like the ocean. Let's take a listen to this one. It's back on noise. Listen to that. I use this thing as a static generator. So just think if that was in an audio circuit. Very, very noisy component. Quite the difference. So the noise circuit works very well. The nice thing about the wattmeter circuit on this is when you put it in the wattmeter, this gets nice and bright. Yeah. It makes everything go quiet. Switches a bunch of things in the circuit inside. And ready to use the wattmeter I demonstrated earlier. That works just perfect. Very, very well. So all in all, I'm extremely happy with this, and I'm glad to add this to the Overtime Workbench. It is coming together, and the visualizer is getting close to completion. That is such an incredible project, and I'm putting smaller projects in the middle so that I can get some videos up for you guys, and of course giving you a break from that because I've also been all consuming. So that's been quite the project. But this one is done, and it looks fantastic and works fantastic. I'm looking forward to using this with you guys, showing you how to troubleshoot circuits with this signal tracer. Very, very happy with the results. I'll share some vacuum tube knowledge with you that a whole lot of people know. I'll start with the filament system here. So we noticed in the signal tracer that the filament lines are twisted together like this and pressed close to the chassis. The reason it's done is to stop the filament system from interfering with other parts of the circuitry to keep it on. This is pretty common. A lot of people do this, and this is pretty well known. So usually this is hard to balance AC filament system, transforming the center tower under the chassis, just a hard balance. So filament lines have to go up to a vacuum tube to light the filaments. So if we take a look at a really high quality vacuum tube, and we look at the filaments inside, so this is a really sought after vacuum tube. You can see the volume diamond on the bottom there. So if we look at the filaments inside, you can see those are white wires. They run up inside a cathode sleeve, turn around and come back out. And it's the same on the other side, because there's two triads in this specific filaments in there, running up into the cathode sleeve and then coming back out again. So again, a very high quality tube. So if you want to take that to the next level, go to something with extreme quality, you can go to this 5751 5-star vacuum tube by General Electric. It doesn't get a whole lot better than this. So you can see the filaments here, they run up inside the cathode sleeve and come back down. Same with this one, runs inside the cathode sleeve right up on top and then comes back down again. Those again, two triads. Now, when we talk about high quality tubes suited for audio, we look at 12AX7, everybody knows what 12AX7 is. But there's the 7025 version. You can see that 7025A. What's the difference in this vacuum tube? Inside that vacuum tube. What's happening with that filament in there? So on that side right there. What have they done with the filament? That's how you spot really high quality audio. If you're ever looking at an amplifier, you want to look for filaments to do that inside. Top quality tube right here. 5691. Filaments inside right there. Another really good audio tube designed specifically for audio. It's a cathode right in the center of that tube. Here. And that's the difference between a high quality audio tube and just a high quality tube. So whenever you're designing an audio amplifier, and whenever you're wanting to search out some really good quality tubes, those are the things you want to look for. You want to look for those twisted filaments. So the lowest time possible. I'll talk more about this in a future video, and we'll actually do some experimentations with hum and all sorts of things. So there you go. So that could acknowledge that. Thanks for stopping by the lab today. I hope you enjoyed me sharing this information with you and the repair of this ST-2 signal tracer. If you are enjoying the videos, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos coming in the near future. We'll be taking a look at vacuum tube and solid state equipment along. So there will be a lot of troubleshooting, repairs, restorations, and even some circuitry design on this channel. So if you haven't subscribed, now would be a good time to do that as well. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way, you're going to want to check out my ongoing electronics course on Patreon. I'll put the link just below the video description. So just below the video description is a show more tab written in capitals. If you click on that, it will expose the link. You can click on the link and it will take you right to Patreon. I'm also sharing many of my designs and inventions out there as well. So there's a lot of custom pieces of test gear that you just won't find anywhere else. Lots of really neat things going on Patreon. Alright, until next time, take care. Bye for now.
should be. Alright, so we did confirm the same thing. You're missing the intro today. New day, laptop repair. It's time. What we're going to do is we're going to try to change the socket on system this year. Is it going to work? Is it going to work? Or not? But watch everything for him. When I do this weird voice, I don't know why. So I was looking at both and stuff like that. I figured out why some of them don't. I don't think it's my voice. I think it's my standard. My ums, my, I can't get out what I'm saying. My talking with my hands. My
butter, wax. I have black horse wax there. What's the best question? Last case, you have individual uses rules, otherwise one is else. Do you actually need one of them? Otherwise, I can take one half if I want. Sure. I'm taking quick information. I'm sorry, I have to take that one. I'm asking for a model of the gas station again. And again, those are in chat. Products is never been strong suit. Reading is not fun. Like, you kind of hunt around and say, okay, I need a good camera for your cell phone. Your cell phone is the best thing you have. You don't have to buy it, but if you just have to buy a web camera, we'll take that dynamic range on it. Or you might have something that's better than the clarity. I mean, the clarity is pretty good, right? This is okay. But even my cell phone, all of the electronics that were on the way to reliable were all my cell phone as it is. 70%. You're squeezing it on, putting too much out, putting it on when it's hot. Don't fix this. I love that.
called chip test. Now, the board is what's on top. Since you're probably 100% off, it's probably correct. I'll get one board that has basic view that needs to be CPU. That is the safety. Come on, give me a second to chill out for a second. That was not as easy as I was putting it out. I was like, oh yeah, it's already hot. Let's just do it. Let's just do it. Back in the chat. Not bad, John. Brown says not bad. I thought it was worse. Now we have Alright, I don't have that. There. down ACQ for no reason. You're not failing. You're not failing. You're not failing. If you're not failing. Right? Wouldn't fail it. It's well, that's what kids know to learn. Pressure. when did, I saw that you had that alert on the design problem, so I decided for my boss to actually just change my camera phone. So I have an explanation for the microscope, an explanation for the overhead, and change the
bad. Real bad. This is a CPU swap, and this is a CPU swap. Sorry about that. Throw it in the trash. Next time we do that, we can do something discuss this. What we need is that whole screen have a white one at the same time with this. Set it forward. Do a return to that. Crap, repair. I can do it. You want to just tell you about how that's not playing. So at least you feel like you got some sort of satisfaction with it. Next Sunday, if I can continue working on this, so we go through and fix all the solder masks and stuff like that. So, yeah, we can I have I just don't know what to do. Like a hammer. I have a hammer. PCH problems on the stuff bother you. Get a flat iron. $2,000 for give me one of your machines. Maybe I'll say it. Gritty, all good for some bits. Thank you, Gritty. Thank you, Gritty. More than 3 hours. Appreciate your patience and guidance. That's good. I feel like I've been enjoying more by doing this. I don't feel like I've done it. I want to do something. It's handy over there swimming. He can fix my TV. He got the LEDs on. Back up. I didn't do anything. I put a whole video up saying I want to install something. I have to install it. Little chat party crowd was on. Let's see what happens. Let's see this one. Client using laptop shut down. What is it? Client using laptop shut down. So this is an Alienware X15R2. And X15R2 is shutting off randomly by employees for siege emissions. So it could just be a big so that'd be cool. Let's look at one more. This one's already more of it. The repair shop took told me to watch the board is overheating and not charging. Which one is it? The logic board is overheating and not charging. Right, the repair shop is that is a XPS 13. Okay, I got a warranty here. That's somebody sold the laptop and they installed most of the Amazon car repair that I did. So
Dang it, Larry!
Right now, many of the drugs that we have, they're extremely restricted, not from just being sold, but from even being flown, all depending on what happens with ongoing government discussions here in the US. But it's not all bad news. We have incredible homegrown technology right here in the United States. Innovative systems being built by American companies that most drone pilots have never even heard. Over the past few months, I have traveled all across the country, meeting with these manufacturers, touring their facilities, and flying their systems firsthand, all to help you understand what's coming next and to prove that there are real, viable American alternatives ready to take flight. This is the US Drone Showcase. As someone who's personally invested nearly $500,000 into DJI systems, I was just as concerned as many of you about the future of the US drone industry. What would happen if we suddenly could buy or even fly the tools that we rely on every day? So I started digging. I wanted to find the best American-made alternatives that could actually meet the needs of real-world operators like myself, someone who's been in this industry for over a decade. But I quickly ran into the same problems many of you probably have. There's almost no information out there. No detailed breakdowns, no comprehensive videos, nothing that helps professionals make informed decisions. So I did what I do best. I took it public. I made a simple LinkedIn post, expecting maybe a few comments. Instead, within 24 hours, I was flooded with messages from founders and executives across more than a dozen US drone manufacturers, inviting me to visit their facilities and fly their systems. That's when I knew this needed to become something much bigger. Unlike DJI, most US manufacturers don't make their own radio systems. They mostly rely on two major suppliers, Zovis and Doodle Labs, and those components are incredibly expensive. To give you perspective, one manufacturer shared their numbers with them, an invoice for a total of about $250,000 for just 40 radios, and that only builds 20 systems for them. Yes, this is a higher-end system that they build, but it still shows how steep the curve is. It's why building a reliable US drone under $5,000 or even under $10,000 is nearly impossible. There are non-NDAA compliant options, like this Early system that I have on my own drone that I built, all for about $1,500. But many of the new service contracts don't allow for these specific radios to be used. The second hurdle is payload integration. Chinese companies like DJI make both the drone and the sensors, so everything connects seamlessly. But in the US, drone manufacturers often have to integrate third-party cameras, LiDAR, and thermal sensors, each with different communication protocols. That can mean 2 or 3 layers of communication that all have to sync perfectly, or risk reliability issues in the field. So while it might look like a simple plug-and-play setup from the outside, the engineering behind that stability is anything but simple. Again, jumping back to the drone that I built, I only had a camera attached to the autopilot, and that's the only thing that's talking. If I had a gimbal in here, it would make it a much longer and more complicated setup, which again runs into that reliability issue. I don't have full control of this. I don't manufacture any of this, so there's a lot of back-end stuff that I have to make work in order for the setup to seem like it's flawless. Where on the end over here, it's just, again, a plug-and-play option. The third challenge is software. Most US companies start with an open source flight software and build custom code on top. It's a smart move early on, but as they scale, that code base can become bloated, slowing down new integrations and updates. The good news is that many of these companies are using their new rounds of funding to develop their own proprietary ground control software, giving them tighter control and faster innovation cycles. These 3 hurdles, the radios, payload integration,